3 weeks. Yeah, no, but that was the reason. So we just started. Okay. Can you hear me? Ah, yeah. Okay. Good. Welcome back after lunch for the first session. The first speaker in this session is going to be Stefanie Reimann. She cannot be here, unfortunately. I guess she's back in Lund in Sweden, and we are happy that she is here to talk about the work on persistent currents, vortices in binary and dipolar BECs from many atoms to the few body limit. Okay. Stage is yours, Stefanie.
Yeah, thank you very much, Timon. Can you all hear me?
Yes. Yes. Yes.
Yes, very good. Thank you. And good evening, I can say. Yes, I'm home in Lund. And I should also apologize really that I could not be able to travel across the Atlantic. I got some health problems a month ago. And I'm super, super grateful to the organizers, first of all, for this very kind invitation, and then also for their understanding and giving me the chance to give this talk now by Zoom. I was really sorry to miss out on this meeting. I was just saying to Simos, it's seldom that all the program of a conference is top-notch on your own research interests, so that's sad to miss. Tilman, I should also say that it's actually you who started this work in Lund. You remember you gave a Rydberg colloquium some time ago in our Rydberg hall, because Rydberg is actually from Lund, and that inspired us a lot to actually try to get into the theory of these fascinating filaments and dipolar droplets that you have shown us. And this will also show the impact on the talk that I give now here. So, very much actually inspired by your lecture back in, I think, 5 years back or 4 years back, just after the discovery of these nice self-bound droplets. To begin with, I would like to remind all of us to the trapped Bose gases in a single component in a trap. You have seen these pictures of vortices since 2001, I think, or 2000 even. When you set a one component Bose gas to rotate, you form vortices due to the superfluid nature of the whole thing, and you get a vortex array if the trap is harmonic, and if the trap is anharmonic, you get then centered at the origin of the trap, but you get these beautiful vortex lattices. Now this is for repulsive interactions, but if you turn the interactions attractive, it forms like a blob, and then if you put rotation to it, this whole blob is boringly slinging around in the trap. And if you make your attraction too large, it actually becomes unstable. Then one might think of the quantum fluctuation corrections, but usually in a one-component system, the size is really small, and they don't have any effect. So this could, at this time, not really cure anything, and no self-bound states were found. And I think in this community, you all know about Petrov's amazing paper from 2015, where he was actually doing exactly that, to take the quantum fluctuation contributions to stabilize a two-component fluid. In contrast to the one-component fluid, when you have two components, you can only tune the mean field so that only a very weak residual part is left. And then this residual mean field interaction balances with the quantum fluctuation contributions and possibly also other higher order corrections, but this would be the first one. There was a prediction 2002, I think, by Bulgak. He went to three-body and Efimov type of things and so on, which was a little bit in the same spirit, but this here really brought it into the realm of quantum fluctuations as the main correcting or stabilizing mechanism. And I show now some almost simultaneous. You see, it's very interesting to notice the year here. This was in 2016, so just shortly after the Petrov paper, and this was for dipoles, when it was known that these dipoles form filaments, they self-stabilize. This is one of the papers, the early papers from Tillman's group. There was a previous one, Padau et al. In Nature, showing also these self-bound droplets. And I think this must have been the things that you showed us in Lund that were so amazing to see, that you really form these dipolar elongated self-bound droplets because of the stabilization through these quantum fluctuation contributions. And when you put them in a waveguide, the magnetostriction makes that when you press from the top, when you have a single droplet, it splits into many small ones. Because of the magnetostriction, it really doesn't like that you push it from the top. And this is what you saw in this paper here, that when you have them in a waveguide, these droplets, they know about each other's repulsion, and unfortunately they then go far apart because they repel each other, and the waveguide is really sort of not the best thing to make them overlap, which is what one wants to do, thinking of this very old riddle of what is a supersolid. When you have superfluids overlapping, you might think that you get this supersolid state that I think has been discussed so much on this conference already that I don't need to spend so many more words on it. This, what you showed us in Lund here, was very inspiring because we thought then, when you have these droplets repelling each other, why not put them in a ring? I mean, the super solid has first been found, as we all know, from this elliptic confinement where you have maybe 3 or 4 droplets and then you put them in an anisotropic harmonic oscillator. You maybe have 3 or 4 of them, and then you can observe the elementary modes and excitations. We thought a little bit different here, and we thought that why not put this on a ring? So our trapping potential is just a toroid. So what you do is you take the usual harmonic oscillator and subtract the constant radius from it. And then you can also have some freedom in the z direction that is nice to play with because you have magnetostriction. So you can make it either like a hollow cylinder, I'll get to that later in the talk, or you can just push very much and make a 2-dimensional slice, which has its own properties. So what you see here is a torus for some parameter of this lambda. If you then have you can play with the dipole-dipole interaction strength relative to the S-wave scattering in the system. That's the parameter that you want to vary. And you can actually achieve all the way from a perfect superfluid in a torus, shown here, to a density modulation. That's our super solid case that has cost quite some attention now, to the droplet crystal. And then when you still go down the line here, you see that you get fewer and fewer droplets all sitting in this ring type of confinement, and then forming here a single droplet eventually. So you get all the way from a macro droplet to a droplet crystal to a superfluid. And what I will discuss very much in my talk now is how does this reflect in the rotational properties. And here the ring is of course very nice. You have heard about squids, superconducting ring structures measuring the rotation and magnetic fields and so on. And this is very similar. I mean, this is like a squid, and it also has been called an atotronic squid, so an aquid. So this is a perfect system for analyzing the degree of superfluidity in such a supersolid. The first thing to do is to look at the ground states and to look at the superfluid fraction. So when you start from the pure superfluid fraction is 1. It's a little bit tricky to determine the superfluid fraction, but here the azimuthal symmetry of the system actually helps us, because then we can use a recipe that was brought up by Leggett already in 1970, that you just rotate it a little bit, and from the response of this little rotation you can infer the moment of inertia, and then this superfluid fraction is just the ratio of purely superfluid minus the ratio between the actual moment of inertia and the classical moment of inertia, which you get by this trivial integration. So when you do this and you raise the interaction strength, you see that the system here, first the superfluid, then the superfluid fraction descends, and you get this density modulation, and finally, actually down near the grain, if you just go further and further down, you will find an isolated droplet crystal. Now maybe those of you who do Gross-Petejevsky, there will be many in this audience, I think, you will immediately think that these values here are pretty large, because in the LHY corrections that you can, as I showed the result from Petrov, but or the suggestion from Petrov, but you can do the same thing in the dipolar case. There are these papers by Lima and Pelster, they worked out how to do this. And if one does this for 2 large values, there are some imaginary spurious contributions. and bluntly we ignore them. And actually when you are at these parameter ranges here, these parameters are not so small, so it's a little bit dubious whether one can actually do that. But let me tell you already at this point that it's a question of how you scale the parameters in the system, and if you choose a different norm, if you choose a different confinement, you can realize smaller critical values of the interaction strength ratio that bring you on a more safe land, but the overall physics doesn't change. So why the numbers are so large here is actually because we didn't realize that this would be dangerous to do in the beginning, but then we found that it actually doesn't change a thing. So this is the reason why I dare to show you these relatively large values of FSDD here, which is the ratio here of the dipole and contact strength. Why are rings interesting? Why on earth do you want to put this on a ring? And actually this brings me to take you back very long time to the 1970s, where people thought about superfluids in toroids, and exactly one-dimensional toroids. There is this amazing paper from Bloch from 1973, who has shown that when you have a bosonic gas on a ring, the dispersion relation develops minima, and these minima occur when the angular momentum equals the number of bosons in the system. And not only that, but it's perfectly periodic. There's a proof for that, so you can mathematically show that this perfect periodicity exists. And at these minima, you see that there is a barrier to the non-rotating state. So physically, this means that once you are in such a minimum, you are protected from decaying to zero angular momentum if you have no dissipation in the system. And this periodicity is what we also call Bloch theorem, not to be mixed up with the Bloch theorem in lattices, of course. So this is very inspiring, and it was actually 2014 that this was shown with single component contact interacting Bose gases. This is a picture from, I think, from the group of Gretchen and Campbell, who was one of the pioneers in this field, and they used ring-shaped confinement, and nowadays it should not be any problem to realize this in experiments. And then they take a laser and stir the condensate in order to inflict angular momentum on it. So basically, and this is a little bit funny here, this looks like a big sausage, right? So like a Iona curve, or what we call in Sweden a Falu curve, that you have this constriction, which is caused by the laser stir, and then you move this constriction, and so of course the superfluid doesn't care until you do it fast enough, and then you get all kinds of mess happening. But as long as you do it slowly, nothing really happens. When you do it faster, you can inflict a phase jump on the system, and you get persistent current. Very similar to the picture by Bloch that I've shown you. So when you then realize that you have a metastability, for this I would like to go to the next slide. This metastability, this is the second little minimum here. So what is rotation? Rotation means subtracting minus L omega from your Hamiltonian, which means that you basically tilt the energy in various angles depending on how large is omega. So you can actually reach a situation where you shake the system out from the minimum, or you shake the system into the minimum. So eventually, by doing this up and down, there's hysteresis in the system. As I said, these results go quite long back in time. There's a theory paper by my colleague George Kavulakis here that who analyzed this theoretically, and then it was very much in the works of Eckel and Wright and Ramanathan and other people doing this by now almost 10 years ago. So now we ask the question, what happens if I do the same thing for a supersolid? Dynamical steering is difficult, I'll get to that. So let's first of all look at rotational ground states. All we can do at this stage here, unfortunately so far, is that we can do Gross-Berdievsky and the extensions of it. So we do an extended Gross-Berdievsky where we incorporate the quantum fluctuations in a local density ad hoc manner, because simply these systems are so large, it's in 3D, that all efforts so far to do this ab initio are bound to fail. We are working presently on trying to get an ab initio in terms of coupled clusters, but this will come hopefully in the next 1 or 2 years to realization. So far we only have extended Gross-Berdievsky. If we do such a calculation, we have the freedom to restrict the angular momentum by a constraint. Normally it would just iterate self-consistently into the minimum, but one can strict by a boundary condition the angular momentum, and then I can plot what we in Sweden call the Urast line. You know, it's known from nuclear physics that you ask yourself, if you choose a certain energy, what is the most dizzy state? And Urast means the most dizzy, you know. Ur is dizzy, and then Urast is the one that is most dizzy. And this was a concept developed in nuclear physics back in the 70s also, actually. So this is the energy as a function of angular momentum. And when you are deeply in the superfluid regime, the ratio of dipole and contact is 1.9. You see that the superfluid, there's a vortex actually entering the system upon rotation. So you see the density here opens a gate, lets the vortex pass. You see the phase picture down here. The white lines are the contours of the density. And then the vorticity sits at the center of the track. So right in this minimum here, you have a vortex in the middle of the superfluid. What is a little bit intriguing is that when you raise angular momentum in the beginning, you already see that you get this modulation of density here, because the rotation here is mixing up with the excitations. We'll get to that. Now let us increase the dipolar strength across the critical strengths, where you see here that we go into, when you remember the picture of the superfluid fraction, this is where localization starts to happen. So now something fascinating happens, namely that you get a shift in the curvature of these so-called Urast lines, that you go from this down-bended structure to something that has local minima and looks like intersecting parabola. We plot the density of the Gross-Pedelsky and also the phase here, and you see that initially the phase reflects just a solid body rotation. So you have this whole crystal of droplets that is rotating like a classical rigid body in the system. And now it passes this maximum, goes to the next minimum, and you see that the vortex has entered. So now it carries vorticity, so you have both a superfluid that carries a vortex, and you have the solid body rotation of the system. And that, of course, doesn't really match, because to have L over N equal to unity, you would have to have a larger superfluid fraction. So the only way to compensate for is that we have a counterflow in the system that takes up the remaining angular momentum. And then when you are at the unit vortex, you see really that the unit vortex here is completely established at the minimum position. This game goes on if you still increase epsilon, and I remind you that these values, they might seem very large, but we tried it with other sets of parameters and we found similar behavior. So the largeness, and maybe forbiddenly large these parameters are, it doesn't really affect the overall results of this, what I'm going to tell you here, namely that you have this transition from the superfluid to a more or less rigid body motion when you have a completely crystallized droplet lattice. I told you before, let us remind ourselves about the picture of hysteresis, that you have a hysteresis loop in the pure superfluid. If you have just a homogeneous superfluid, you can rotate it up to a certain extent and nothing happens until the angular momentum jumps and you arrive at the unit vortex. But then again, nothing happens and you get the second vortex and the third, and so on and so on. And since you have this bistability with a metastable state, then this leads to hysteresis, and the hysteresis here first starts horizontally, jumps up, and goes back and jumps down. Now in a supersolid, this is a little bit different, because you have both a classical rotation and a superfluid rotation, right? Or non-rotation, I should say. So the classical rotation here gives rise to a slope that is proportional to the solid body part of the moment of inertia. So you see, you slope up linearly, jump to the next vortex, slope down, you arrive at a different state, and if you do this for different superfluid fractions, you see that you actually get a different size of this hysteresis loop that is in a way proportional to the superfluid fraction in the system. And it's a simple consequence of this bistability, where you have the two minima, one at zero angular momentum and one at L over N, angular momentum over the norm, equal to unity. Now, In the beginning, I showed you results for a homogeneous Bose condensate stirred by a laser dynamically. What I've just shown you was actually the static results that you ask for what is the ground state at a given track rotation. Now I ask a different question. Can we actually dynamically steer the system? And this is, for my taste, a very daring thing to do, because we do this in Gross-Bedejewski, in a dynamical, time-dependent version of Gross-Bedejewski, which, for me, coming from an Aponisha direction, is always like a little bit doubtful whether we can do it. So the main message is we should do it gently. We should not do it too fast, and we should not do it too violently in order not to violate Gross-Bedejewski. But again, since these systems are so large, I wouldn't know anything better than to do a dynamical time-dependent Gross-Bedejewski. So here you have our system. You see the dipolar crystal now in a little bit more slim ring in order to get rid of this nasty epsilon problem. So we decided to change parameters a little bit. And then in your ring potential, you can actually make what we call a weak link by having an angular dependent frequency term here. So you have the confinement that for some angle it narrows in. And you see this here in the red areas. The confinement really pushes the ring a little bit together. So you have a region here where you have a constant ring confinement, and then you have this narrow region with the red color here where you see a constriction. So basically you take this constriction and now you rotate the system. This is a little bit similar to another related problem that we are studying right now. This is when you have capillary flow. So you have a small thin capillary, and then this super solid has to squeeze through. So what happens to these droplets? And this is a similar question here. You have this bump, and the bump is pushing the droplets, but it's also pushing the superfluid. But as long as you push slowly, the superfluid part doesn't care, but certainly the droplets care. So the question is, who wins and what is happening in the system? So before we actually start to dynamically rotate this, I would like to show you that this link has drastic influence on the density distribution. If you look carefully here, you see the yellow line. This is the pure superfluid case. It develops a little bump here. You've seen this before when I showed you the phase plots and the density plots. You saw that when the weak link enters, you get, or when the vortex enters, you get a little bit of this raising of the density close to the vortex entry point. With the weak link is very similar. You see an increase of the density. Then this is the link here, so it causes some depletion of the density, and you can then increase the dipole strength, and you see that with more and more dipole strength, this well-known droplet lattice is building up, right? So you see that they get a sequence of maxima here that very well resemble the droplet structures. But where you have the weak link, the droplets are pushed. One can also understand that this maximum here gets a little bit elevated because the dipoles, they're repelling side by side. So then close to the empty region, there is a little bit more room to accommodate more dipoles. That's why these are a little bit larger. If you have a thin link, there are some commensurability effects. You can make, in a way it's very interesting because the dipolar supersolid itself makes the link intrinsically. This is like an intrinsically built-in Josephson junction that has many, many real occurrences. So you have as many of these junctions as you have droplets. So when you make the link thin enough, it will actually not disturb the droplet lattice too much. So the size of the link, the height and the width of the link is very decisive for its physical behavior. What I will look at first now is actually these Uras lines again. The Uras lines are moderately affected by the width and height of the link. You get a very similar picture for a wide link and the thin link. But you see here the same pattern that we had before, that when you have a perfect crystal, or next to perfect crystal, I should say, you get these two branches. We saw that the first branch is only classical body rotation, and the second branch is then classical body rotation plus superfluid unit vortex. When you approach the superfluid regime, you see here for the yellow regime, for smaller values of this dipolar strength parameter, it resembles very much the superfluid case, but now this has a little bit shifted maximum position. and gets rounded off from the position of the weak link. There's a very interesting difference between the superfluid and or next to superfluid, I should say, and the crystallized region or next to crystallized region, because you see that in the more superfluid case, you open a gap here. So you have the next excitations, you have the next branches, and you have a decisive gap, which makes it possible to have a two-state model where you have two possible transition states here. And this has actually been suggested with just superfluid rings as a qubit realization. So this is quite interesting from that perspective, actually. But when you go more and more super solid, this behavior changes. You lose the gap, so to speak, and you will have another branch here with other crossings higher. So these Euras lines, they are interesting, and they are very similar to what has been seen in general for single component gases with a weak link. Now, let us do this story dynamically. So we take an omega start at 0, and place our weak link in the dipolar supersolid, and then we start to rotate. Now the omega is increasing here until 250 milliseconds have passed, and then it stays at a constant level. What you see here is the angular momentum that comes out from the calculation, and you see that if omega is not too large, you see a little bit of wiggling around. But if you are above a certain critical strength of the omega, you see that it eventually takes the first vortex, and it also eventually takes the second vortex. And to make this a little bit visible, I have brought you some videos here. And so what you see here is the supersolid with the weak link on the left side and the phase picture on the right side. And what you can actually see is that if omega is small enough, nothing really spectacular happens, apart from a little bit of wiggling, a little bit of change in the phase, but not really much. You see, if you look very carefully, you see that these droplets, they move back and forth. So one has, by putting this little bit of weak link rotation, already excited a little bit of one of the low-lying modes showing back and forth. So it's like a swinging mode. The droplets start to swing. Now, let's do this for the higher rotation. So you see here, now we go to the case where you get two vortices, and you see what is happening. That first of all, maybe I should show this again, that first of all, not much, you get the swinging back and forth, but suddenly you start to see a depletion at the position of the weak links, and this depletion then travels around along the circumference of the ring, and you have also in the phase, you can see a clearly established two-fold vortex, which fits well with having an angular momentum of 2 units per norm here that has these small oscillations, because we are still driving the system. Now we do the same thing for thin link, and you see it's a little bit different. The main difference here is that the thin link actually manages to first overshoot and then settles to unit angular momentum, but also when you do a faster stirring, it becomes again very similar. So let's look at that also dynamically. So you see, first of all, nothing happens, and then you get a very clear two vortex in this region here, but eventually then the one vortex leaves and it settles down to a one vortex solution. Same game again for a larger omega. First of all, nothing happens, but then you see very clearly the swinging back and forth, and also you see very clearly this density depletion in the system. And I forgot to say actually that everything is plotted in the rotating frame so that we don't get confused. It's just that the weak link has a certain velocity, and then we go into the rotating frame by subtracting exactly that rotational term from the outcome. Now, it's very fascinating to think about these excitations when you stir fast enough. So what I have here is now a plot of a radial density. You see I plot the density along the angle around the circumference, but I also integrate over the radial and z direction. So this is like it's not a three-dimensional density integral, but it's like a angular density, what you might want to call it. And since one dimension is missing in this integral, everything has units of 1 over micrometer. So this is what is shown here, sort of the density along this rim, so to speak. So you see that first, when you begin to rotate, not much happens, but then you actually realize that there's a depletion here, and this forms like regular patterns. You see these downslopes? And these are solitons forming out from the state upon rotation. So you see, you first have a homogeneous superfluid, and when you rotate fast enough, you see that the density modulation sets in. So it's kind of that this rotating link already sort of manages to excite the system and mess around with its photons and so on. I can show this again. So you see, first nothing happened, and now you rotate too fast, and now you get this depletion. And you also see that this solitonic wave-like thing is remaining here for many repetitions. You have this density depletion. This is, I think, the more fascinating case, to see this density modulation originating out from the purely superfluid regime, but we can actually also go into the more supersolid case. So here you have this very well-known supersolid limit, now in a toroidal structure. And again, you see the solitonic lines forming, but now everything becomes a little bit more messy. So let's look at the movie. You see, there is the weak link manages to irritate the droplet that is enough so that it spits off smaller droplets that are then messing around with the rest of the localization, and you have a soliton that is a solitonic wave-like structure that is circulating in the system. So much about the dynamical rotation. It is also interesting to imprint vorticity on the system and then just switch off the trap. This is what I show you here. This is a simulation after imprinting several units of quantized angular momentum. Then you switch off the trap, and since the dipoles are repelling each other, in this case here, when you have a non-rotating system and you let them expand, some of them will move inside, some of them will move outside. That's why you have a maximum here in the center. And please note that this is a supersaturated scale here, so that white means white on both ends. So this is actually a maximum at the center. It's been very difficult to plot this in a better way, so this to cope that this looks almost like a white spot, but it's actually a maximum with a yellow spot. And now, when you go to higher levels of quantization, you see a relatively dramatic hole developing at the center, and upon expansion, this hole should actually become seeable. I think if you would do this in an experiment, I would hope that one should be able to see that you get a minimum of a hole here instead of a maximum at the center of such a trap. This so much about rotating a usual dipolar supersolid. And again, for this audience, I almost don't dare to show these slides, because I think from these papers, almost everybody is in the audience. So I can only wave hello here and say that this is fantastic. We were very excited to see all these things happening. And we as a theorist, we love the idea to be able to manipulate the dipole-dipole interactions, that not only you can change the strengths and all that, but you can actually also change the sign. I mean, this is fascinating. This is fantastic. So what usually is repulsive when you have side-to-side interactions becomes attractive when you have head-to-tail. And that's, of course, very intriguing for us doing all these Gospodevsky simulations. And I was reading with a lot of excitement and fun. I was reading a thesis here from Tillmann's group. This is a Wenzel's thesis from 2018, you see, so this is already quite some years back. And actually it has been lying on my desk for quite some time, and then I forgot about it, and then I took it up again. And he has been describing this very interesting case of pancakelets. So he says, I think at page 93 or something, he says that if you actually turn around the dipole interactions, you get pancakes instead of eggs. And this is very interesting now, I think, when we look at supersolids and vortices. So this is what we did. Now we took up this suggestion and simulate what happens actually when you change the contact interaction so that you get into this supersolid range, but not in the forming eggs, but now forming disks because of the same change sign of the dipole interaction. What you get is it's a lattice of overlapping disks stacked on top of each other. Now, dipolar stacks are not so new. I think this has been done with optical lattices, cutting a dipolar gas and seeing interactions between different slices. It's also been done with electric dipole moments. Luis Santos has been publishing a paper on that, I think. And now we do it just with disposition, just by changing the direction. So, and this is the phase diagram that you see here. So you get really different ranges of parameters where you see a difference from isolated droplets to supersolid stacks and to regular superfluids. Now, the usual thing to do to sort of estimate the degree of supersolidity is to look at the contrast. It's making a smooth transition from unity, where you have a perfect superfluid, then to zero. And the same as you can do by using Leggett's upper bound and calculate the superfluid fraction. This way, the two methods are sort of complementary, nothing new in that. And you see the same thing happening, but just with opposite sign. And then, if you plot the density profiles here, you see that there's an intersection point here, and you can think. I mean, when does it make the transition from one blob to many and to the supersolid? And this is difficult always to estimate from just looking at the density distributions. That's not really a clear sign. The one way to do it is, of course, to do a linear response type of thing and calculate the Bogoliubov excitations. And for this case, they are particularly clear, I would say. So you see that the mode going down and up again here, the X-like thing, and then the Goldstone thing, and you see that really here at this point you have this crossing of branches, which coincides with the point when you see in the density that it changes from homogeneous to localized. So now you may ask that, okay, but we already know about superfluids, so why is this so interesting? And for me, the interest comes when you think about vortices, because vortices are much nicer to look at when you have something flat that you set rotating. It's kind of annoying to look at vortices when you have a flat trap and then you have the X in the middle and then you see the vortices in the interstitial regions, and it's a mess. You don't know what is like just a minimum because of all the X, or you know, is it a vortex, and then it disturbs the X, so it's kind of difficult. But if you just turn it around and look at the stack systems, the vortices should be much more clear, I think. And we are presently trying to find ground states for these systems, ground state vortices, vortice lattices, and so on. I can only show you here today some first results about imprinting a vortex. Here is a twofold quantization. And this, because it's imprinted, is only at the center, but I would think that these would actually make a vortex lattice. But when you imprint them, you see that the point here where you build up this supersolid structure, where you start to build up the crystallization, leaving the pure superfluid regime, shifts actually for increasing vorticity. So you see that all these curves here are shifted to the left, the higher the quantization is. Now you may ask, what happens actually? This now I tell you something that is super exciting at the moment, and that we are evaluating this full speed, and I hope that in the near vicinity of time we can have a manuscript out on this. When you have persistent current in a single ring, right? And now you split it, what will happen? I mean, will the persistent current distribute on all the stacks, or will it just remain, or will you get solitons, or what is going to happen? Now I see time is running out.
Yeah.
I'm late, but I will can I flash the last part?
Yeah, if it's 1 minute or so, yeah, then it's fine. But
yes, I mean, it will be 1 minute. 1 minute, very short. Let me just flash the last part. I think the Zoom talks are a little bit more difficult to know the timing. So, but I would really love to show you, because now we go ab initio, and I just remind you now of this paper by Petrov. This was not for dipolar, but for contact. And we do now the same thing, but let me skip this one. But we do it in the few body regime. It's not only, I mean, when you go to low dimensions, you don't have this atom number restriction that you need tens and hundreds of atoms to make a self-bound state. But in low dimensions, you can get them already for like 2 and 3 and 4. And so we said, okay, let us try to do this thing exactly without resorting to all these dramatic ad hoc approximations and diagonalize brute force. So we have developed diagonalization tools to map out the exact diagonalization results, which compared to other methods like quantum Monte Carlo and so on has the advantage that we also get the excitations. This is big, so this is our old computer, now we have a new one, but we got this actually also this month only, so I don't have a picture of it. And what you see then is when you look at pair correlations in these exact densities, you see a dramatic change from the few body superfluid to a localized state. Very similar to what we have discussed for droplet formation. And when you do a corresponding Bogoliubov analysis, you see that it happens sort of in the vicinity. If you look at the excitation spectrum, I showed you Higgs modes before, I showed you the occurrence of the goldstone, and actually these are interesting precursors. You see, you have a monopole mode here. These are the excitations, low-lying excitations. You see, you have this precursor of the monopole mode, and you have these higher angular momentum modes that actually collapse down to zero when you increase the particle number. So these are very interesting precursors, and we think it's very exciting to see. And this links actually back to work that we did together with Cecilia Jochen and his group to study how do these phase transitions emerge atom by atom. I mean, what is the few body analog of these beautiful things that we have seen? Now the droplets, we know they only exist for large atom numbers, but you can go to low dimensions and study this actually in a different setting. Also, the rotational behavior here is similar. This is the last thing I want to say, is that you see that you get the superfluid behavior changing over to rigid body rotation upon self-binding of this system that is made by 4 and 4 atoms. So these exact diagonalizations, they would then be a great asset actually to study things like superfluid drag and related effects. And with this, I would like to thank you for giving me the opportunity to tell you these things here in Zoom. I'm very sad that I cannot be there. And in order to make up for that, please, if you have questions or want to discuss more on this, we could just by email arrange a Zoom meeting and then discuss it face to face. Thank you very much for listening.
Thank you, Stephanie. And we have time maybe for one question, if there is a question here in the audience. Yes, please.
For this last few body stuff you showed, like these spectra, if I remember, like, so you said they're ED spectra right now, so you have all of the states basically there, and then if you do the dynamics, did you ever calculate, say, overlaps of your dynamical state with the spectrum you have available now? And how does it mix the different modes, basically, when you do the steering in the different regimes?
Yeah, thank you very much for this question. Actually, this is what we are doing right now, because the exact diagonalization that I've shown you was only static. But with the method that we have been developing is actually allowing a full quantum dynamics also. So I think the next step would be then to actually have such a dynamical rotation of a weak link and see what the exact quantum dynamics is going to do to the state. And then I think there's also another example which is super interesting, is that you can have a disbalanced system. So you can have an unequal number of particles. So you have like n prime bosons from one kind and double prime from the other kind. That means that you form a droplet inside a superfluid. So you have a compound system. And that you can actually build if you like 6 and 8 or 10 and 12, it would already show you the dominant features of a larger system. Now what we found from Gospodyevsky or from extended Gospodyevsky is that such a compound system actually already has quite a lot of the super solid properties, because you have one droplet traveling around in the superfluid. So it's not so different from a fully fledged super solid structure. So I think this will be super interesting in the future. Super interesting super solids.
Okay, thank you, Stephanie. I could listen to this forever, as you know, and we should continue this discussion later on. Unfortunately, or fortunately for the next speaker, we have to move on. So thanks a lot again. And
thank you. Thank you for having me. It was fantastic to be able to do this via Zoom.
Okay, yeah, thanks for being with us. And
Yeah.
We
I'm sad to miss out on all the other things, but hello from here, hello from you.
Yes. Yes, and we are continuing now with the talk by Valentin Walter, and we have to get him set up here.
See you.
He's going to talk about, as far as I remember, three-body Rydberg physics, something like this.
So first of all, I would like to thank the organizers. It's been a real pleasure being here, listening to the exciting talks yesterday, this morning, talking to people, and also just being back. I will talk about Rydberg interactions beyond the binary limit in two different systems, and these are two topics that I've never talked about before. It's work in progress, definitely unpublished, so I'm very much looking forward to your comments, your thoughts, and input. So I want to just, maybe on an ironical note, and maybe not quite, start with this picture here of a colony of penguins who live in Antarctica, obviously. And so it's a cold place, and to keep warm, the penguins kind of need to optimize their body temperature. So they have an optimal body temperature, and to make it easier, they form groups. Now, as you might see already in this picture, they don't stand directly next to each other, and this is because they would overheat in this case. And it turns out, as this paper will tell you, that the way penguins optimize their group structure, a colony structure, is that they move along the gradient, or the heat gradient that they perceive, and if they're too cold, they will move up the heat gradient. If they're too cold, if they're too warm, they will move down the heat gradient. And so it can be shown that this kind of procedure already, if you want to model it, does not only include binary interactions, it also includes three-particle interactions. And so they use that for thermal regulation. So in physics...
Just a second, could you just put the mic?
Oh, I'm sorry.
Okay.
What does Albuquerque mean? It's in New Mexico, right?
Yeah, I was confused about this too. But I didn't go to the bottom of this. So, I mean, they have the nicest penguin pictures. So I guess it's a zoo or something. I don't know. So in any case, maybe I should go to something that I know some stuff about. So in physics, three-body interactions appear often as some sort of emergent interactions from underlying two-body interactions. So for example, in the classical three-body problem of...
Can you open the
switch it on too, yes, yeah.
up there? Yeah.
There's a knob here.
Great. Okay, so does this work? Okay, great. So you will see that there are three-body terms appearing in this classical gravitational problem if you treat extended objects such as planets, for example, as point particles. So that will induce, to describe things correctly, then you need a three-body force. Also, in nuclear physics, there's a three-body force that binds the nucleus together, and as I learned, it makes up 10% of the nuclear binding energy, actually, especially for heavy nuclei. And then, of course, in quantum physics, there are Efimov states famously resulting from collisions of three particles with short-range interactions and giving rise to an infinite series of bound states. Now, I will
like talk about different systems and connect back to like topics that we heard about yesterday, dipole interactions, and kind of try to, in the spirit of the conference, try to unravel like emergent interactions in van der Waals systems. First, like looking at Rydberg lattices, and then at Rydberg macrodimers, which are giant molecules, and I'll introduce them later. So let's get right into the matter. So three-body interactions, sorry about that, in Rydberg lattices. This is work I together with Ryan Samajda and Misha Lukin. Okay, so like looking back at van der Waals interactions, where do they come from? Just like a quick recap, like let's say like we are looking at two NS states here, and we have this dipole interaction here in the near field limit, so no retardation that we heard about yesterday. So what do these systems do, or what, like there's no first order interaction, but instead like there's a virtual transition to some other p states, so it could be belong to a different quantum number, n prime, n prime prime, and back. And so what I want to draw your attention to is that what matters here is the energy difference in this virtual process called the first order defect between the virtual states and the original states. So now that's like the more realistic picture. I'll simplify this to just keep it to a simple model here. So we start from some SS state. Now I ignore that the p states can belong to some other principal quantum number. It's some p state, and there's a first order defect. So binary interactions then are just like a virtual hop, basically going from SS to PP and back. Now if we have three atoms, right, like now there's not only particles 1, 2, but also particle 3. Now this state, like in the ground state, SSS state, could hop up on the first with the first two atoms. So you can go to this PPS state and back, PSP using particles 1 and 3, or like van der Waals interaction 2 and 3 and back. And so this gives like kind of a sum of two-body interactions. But then, as you will see, like kind of the same interaction, the same dipole Hamiltonian will actually also induce interactions between the excited states. So for example, if you have virtually excited to the state PPS, then the flip-flop interaction here, 1, 3, can transition you to a state SPP on these states. So there are all of these connections too, and you can already anticipate that this is the origin, like, you know, where three-body interaction can now emerge from the underlying two-body interactions. Now, this has been looked at like back in the day. So the first consideration of this effect goes back to the 1940s to Axelrod and Teller, who wrote that the general interaction of three atoms in their S states in a simple model takes this form. And you see here already that they're always like kind of the dipole, the action of the dipole operator appears 3 times in the denominator. So it's a perturbative, it's a small effect. Then much later, there were there was a discussion in the literature around like 2010, 2015 about Borromean reactions, where 3 p states can come in and they react to 2 s states and another p states, but only in the presence. I mean, like you cannot just subtract this from both sides of the equations. Only in the presence of this additional Rydberg atom can this reaction occur. And then Thomas Pohl and others have like looked at Floquet engineering, so driving with Rydberg fields, you can also try to manipulate this interaction. So we will take a different route here, a slightly different route, and look at the many-body interactions in a simple model. So what I show you here is just the expansion of the dipole-dipole interaction in general, and like you see, like all the pairs of atoms, like their interaction depends on the angle theta that connects them with respect to some quantization axis. And so let's make our lives easy for now, and let's say like all the atoms that we consider sit in a plane, and we choose the quantization axis perpendicular to that plane. So in that case, theta is just 0. It's just pi over 2, and this entire model becomes very simple if we also assume that the atoms are dipole, or like two-level systems, so we have only one transition, one S state and one P state. And so now looking at this, it's already a non-trivial question to ask about like how large are the 3-particle interactions? we saw that they in principle should be there. 3-particle, 4-particle interactions and so on should also be there. How large are they? And it turns out that like this is actually something that you can look at in perturbation theory. So the many-body interactions can be like using von Vleck theory. You can write an effective theory now for the atoms in the S states. And here you see like these are the van der Waals interactions that we all know. So this is a second-order effect. But now I write this to 4th order, and then you see already on the 2-particle level there's another contribution to the 12th. So this is the 4th order contribution. This is the part that looks at 3-particle interactions with 3-particle terms of this shape and 3-particle terms of this shape. And in addition, then there are, of course, at 4th order, the first 4th order terms come in where particles excite and then hop and then de-excite. So you have all of these contributions, and we see that like kind of as we go higher, this is a perturbative expansion, right? Always the higher order terms are suppressed in the 1 over r, like in the separation between the particles. But on the other hand, you see that there are sums over all combinations of different particles. So while each term in the sum is suppressed in this perturbative expansion, the multiplicities of these terms grow. So you get more and more states of each of these contributions. So here I just want to show you like a little example, like how we understand these or one can understand these systems. So let's say like I have a chain of atoms and I calculate the ground state with respect to this model Hamiltonian, and I calculate an effective theory to nth order. So here up to 9th order in perturbation theory. That's then of course done on a computer, and you see that there's pretty fast convergence for large atom numbers. Now, if you go to other geometries, say a ring or like some atoms in a square, you see that the convergence here is not quite as good. And in particular, when you go to something that resembles a square and like becomes much worse. So convergence is quite slow. So what I want you to take away from this like little like simulate or like model system here is that higher order interactions beyond the 2-particle limit are only relevant when the particle-particle separation is very small, or when the connectivity is so like when each particle has many neighbors. And in the typical limit that we have in many experiments, this is not the case. So we're in this limit where particles are far away, there's a low connectivity, and hence the 2-particle limit, the 2-particle interactions are so good, and that's why we understand most of Rydberg physics just with the binary interactions. Okay, so having said this, let's go back to specifically 3-particle actions and look at ways of like how could one enhance now the 3-particle contributions that we saw were generically small. And so here's an idea of how one could do this. Let's say like you detune one of the components, let's say the PPS states, you detune that optically, for example, and at the same time you make the hopping rate V1 too large. So now this contribution is suppressed, like the binary contribution is suppressed because this state is detuned, and at the same time, like once a particle virtually hops into the state PSP through application of the dipole Hamiltonian acting between particles 1 and 3, now, because this interaction is large, it's likely that it will hop over to this one before going down. And then you have included all 3 particles, and you have actually reached a 3-particle interaction. Now, you can also think about this.
So
Yes?
can I ask, so should I think about all this description like a 3-body system, just 3-body, or not?
I mean, these are 3 atoms. I'm showing this for 3 atoms now. But you can generalize this to many-body. It's just a perturbative many-body
Yeah, but the
calculus.
analysis here is on the 3-body level.
Mhm.
That's it. Okay.
Yes. So you can think about this as like kind of basically if the interaction V12 is very large, think about this as like some sort of splitting of these 2 lines that then can interact with the state 1 SSS. Okay, so how could one do this realistically? Because this detuning here, this first defect that I introduced in the beginning, is typically very large, so it's difficult in the lab to just like detune one state. So what we thought about is to just minimize this energy scale in the first place, which you can do by, for example, going to a first resonance or like some atomic conditions where this delta is very small, and then one can think about shifting the state, for example, PPS with an AC Stark shift, and then using a first resonance. And now, like, I'm slowly leaving the model character of the description, going back to rubidium, where we then like evaluate this theory. So in rubidium, there's this first resonance that can be used to just make this delta in general smaller. And then let's say like you can also put in a small magnetic field just so to split some of the degeneracies that are there, even for the 2-particle system, but even more so for 3 particles. Okay, so here, what you see here is a 3-particle ground state. So here, 37S, 37S, 38S. And you might say, okay, well, that kind of looks very familiar, right? Like it's just another van der Waals interaction that as the distance between particles 1 and 2 is decreased, just drops here. But in fact, in this calculation, the binary interactions is the blue line. So without real 3-body interactions, there is actually basically no interaction. So what happens here is that like a split state from another state comes down, and this is a true 3-body interaction thanks to the conditions that we have here. So kind of now how do we understand this the system, and how do we maybe like use it for whatever application we have in mind? So let's think about qubits. So every atom can now be in a ground state or in a Rydberg state. So this would be this S state. So this is the manifold of one Rydberg excitation. Then there are states with 2 Rydberg excitations, and then there's the state with 3 Rydberg excitations. So the state with 3 Rydberg excitations, that's the red state that I showed you on the last slide, and it interacts with this other Rydberg state R prime. And so through this 3-body interactions, these states will hybridize and mix. And so let's say like if we're interested in the ground states of these systems, let's say we want to go back to a qubit system. So in this case, one could try to eliminate the state here. And in that way, like you get this very long Hamiltonian, or this very extensive Hamiltonian that has like actual 3-body interactions. It also has conditional 3-body interactions, and it has like these interesting terms that are conditional spin flips, basically, that only flip the spin when the other 2 particles are in the Rydberg state, and it has flip-flop interactions that are conditioned on the 3rd particle. So with this, like kind of you see like there's a lot of control in all sorts of parameters. There's the detunings, there's this mixing angle theta between the 2 lines, and so on. So to illustrate like kind of what we tried to like just distill the first features that we might see in the system, let me put this on a lattice. So let's say like these 3-body interactions now act between these 3 atoms and also between these 3 atoms and so on. But let's neglect 2-body interactions altogether, which we saw in this example were small anyways, and let's fix the mixing angle just as at theta half. So that would mean that we're just exactly at this crossing, which you can adjust experimentally, but just by placing the atoms in the right positions. And so then let's look at the phase diagram. So as a function of the detuning and the 3-body interaction V, like what would be the ground state of the system? And the first thing to look at is here the classical phase diagram, where we neglect all the terms that do spin flips, and then you will see that there's like a large section with no excitations. So all the atoms in the ground state, there are 3 excitations when the interaction basically wins. So like when the interaction makes it favorable for the atoms to be all excited, and then there's a small region with 2 excitations. Now, Ryan ran some DMRG calculations, including the quantum effects in this model, and you see basically qualitatively it's similar to what we saw classically. So there's a big region with low excitation, so atoms in the ground state, then there's like some fairly high excitation, and then there's this region with 2 excitations. So like this is how we can think about these phases.
What is the color back here?
The color is n, like kind of n in z direction, like kind of the population in z of the qubits per plaquette, so per triangle. It's maximum 3.
This is 3 atoms again.
This is like, it's a lattice of 25 atoms,
25.
but I took the average over a plaquette, so
Okay.
it can maximally be 3. And so now we can look at, okay, so one maybe interesting point is here in this ground state, this phase is actually like has one atom that's polarized along z, and the other 2 atoms are in a triplet state of a superposition of being excited and not excited, giving the total of 2 excitations on the plaquette. And so now we could like kind of make all sorts of analysis, and we're not finished with this yet, but let's say like we make a cut here through this phase space and go from left to right and look at some other observable, let's say sigma x. So then we see that it comes from like an unpolarized state, it goes to another unpolarized state, but in between, so like somewhere here on the space boundary, you see some sort of polarization in x.
So, so now you have a lattice,
Mhm.
right? And you assume that you are translation invariant, or
Mhm.
this is for granted? So what I mean is that now you have these plaquettes,
Mhm.
and you assume that it is homogeneously, your spin state is the same in all plaquettes. Right? You assume translation invariant?
Assume this for the DMRG calculation? No, it's a finite size effect, so we actually fix the boundary. So the like this is like kind of numerically we see that like one particular state that we fixed on the boundary is the one that is like in
so
the...
what I mean is it obvious that you are going to have just that all plaquettes are the same?
No, not necessarily.
So you have hard walls, really?
It's hard walls, yeah, but
Periodic.
not periodic yet, yeah. It's maybe a good point, right? I mean, it's not obvious that it's all the same, to me. And we see that like kind of there are fluctuations here at this, exactly at this phase boundary. So then like one thing that one can also look at is like, just calculating entanglement entropy. So how much cutting the system basically in 2 and calculating the entropy of the bipartition. And we see that there's like along the phase boundary, there's some entanglement here. We're not quite sure yet like how to interpret all of this, but there's definitely like one point, like kind of where the 3 phases meet, like kind of with the different numbers of excitation. There's like a lot of entanglement here. And so we're thinking about like characterizing this better, like kind of the quantum behavior, the effective field theory that one can maybe formulate around this point. Okay, so I wanted to show you that there are interesting effects that can happen, emerge from 2-body interactions in Rydberg systems. And now I'll just slightly shift gear and talk about like something that's very much experimentally motivated. So like here I worked together with Simon Hollerith, who did all of the measurements as part of his PhD at MPQ. In Emmanuel Bloch's group. Okay, so in case like we've yesterday like already heard a bit about molecules, but in case you haven't heard this macrodimer story, it's quite fascinating. So let me just give you a very brief rundown. So here we again see like as a function of the separation of 2 atoms, of 2 Rydberg atoms, you have these potential lines. So very much like the ones that I showed you already, but like very often you have like lines shooting up with positive, repulsive van der Waals coefficients, and you have attractive lines like the red one here. But unless there's some special symmetry preventing it, then at every, like basically there are no real avoided crossings. So what you really have is a curve like this. And now it looks already like you have a potential minimum here. So like some sort of trap where the 2 atoms at like some separation could maybe vibrate. And this is actually also what you find. So like you can calculate that there are like these states here, like vibrational states basically of 2 macrodimers, where the special point is that these macrodimers are almost a micron apart. So they're like, they possess all the properties of macrodimer, or like of molecule states, except that they have zero electronic overlap. And so this was also seen, like then back in Munich in 2019, as a function of the detuning laser, you see like this super nice, very narrow series of many vibrational macrodimer states. And so now you might ask, like, what does this have to do with three-body interactions? As I promised, I'll get to that point. But at this stage, what a macrodimer basically is, experimentally, is just a two-body resonance in a quantum gas microscope. So you put a square lattice of atoms into quantum gas microscope, illuminate, and you see here in the experimental figure or reconstructed that there are pairs of atoms that are lost corresponding to the macrodimer. Now, that was the state like a couple of years ago, and in the new iteration of the experiment, the main change was that this excitation scheme was upgraded in such a way that now there's a weak probe laser still going up to the single excitation level, but then now there's a near resonant or even resonant coupling laser that strongly couples this first excited state to the macrodimer. And so the strong coupling here is the new point. So now we're leaving this regime of weak optical probing and entering something where these states can now hybridize thanks to the very strong coupling. Okay, so here this is omega c, like for a fairly weak value on resonance. So we're directly on resonance and probing here with the weak field, and you see that there's a thin line. And then as the coupling strength is increased, you see that there's like some sort of side peak appearing and like cranking up the power of this coupling laser more and more. You see that there are like these deep side peaks appearing. So one can abstract from this and just see that there like the original peak that one saw in the experiment basically gets split into two peaks. And the separation between these two peaks is just scaling with the field strength of the coupling laser. So that's not that surprising with this factor of 2 here because of the collective enhancement. But now here we're just showing the two peaks that are splitting, but in fact there's also the central peak that still remains. And to understand this in a more rigorous way, like you have to actually go back and think about like how these macrodimers are excited from the lattice. And so in the lattice initially, like every atom is trapped in a Gaussian state that is fairly wide on the scales that we're considering. So here, like kind of the first particle is in a Gaussian state that I indicate in this blob, and the second particle is also in a Gaussian state. So in total, there's just a two-dimensional Gaussian state in the two trap positions. Now it's much more convenient actually to not look at this in the coordinates of the first particle and the second particle, but to look at it in the coordinates of the center of mass and the relative motion of the two atoms. Why is this the better frame to look at? It's the better frame to look at because in an excitation towards the macrodimer, the photon basically has no energy or like no momentum, so it will not move the center of mass. But it will change the relative coordinate that then like makes the macrodimer. So basically, you can think about the macrodimer as a state that in the space of the relative coordinate and the center of mass coordinate has the same profile in the center of mass, but has a much narrower relative coordinate. And in fact, it's also shifted slightly with respect to the origin. So it has slightly smaller relative distance. And now when there's like strong coupling, it's almost like a Fano-like problem where this macrodimer couples to this entire continuum of states here in the strong coupling. Okay, so let's go back to the calculations and the absorption line. So here we see like kind of reproduced in theory what is seen experimentally. So it's strong coupling. There are these side peaks. There's a big central peak. And that's basically it. But now we can, like, using this intuition, we can ask, like, what are actually these states that we're seeing here? And it turns out that in the relative coordinate of the two atoms, now on the left you find a state that takes the wave function of the macrodimer. So we transition from a state where the relative motion of the atoms in the ground state was uncorrelated and basically in a wide Gaussian to something where they are very narrow in the relative coordinate. And the same physics happens on the right. You see that again the particles are in a very narrow state. So the entire motional state of these particles is now confined to the narrow motion. You see that there are some wiggles, and this comes from this final theory because they're all the background, or like kind of the continuum of free states that matters on this side, but not on this. And in the center, and that's kind of interesting, you have this line here that isn't shifted by the macrodimer, and it actually can be nicely understood now that it has the same motional structure as the trapped ground state, except that the coupling to the macrodimer basically eats out all the contributions in real space where the particles are correlated on a short range. So you get this interesting state where with wide correlations, except that the short, or general correlations, except that the short ones are cut out.
So this is like a sphere, like a repulsive sphere.
It's like
a hard sphere.
Yes, I mean this is one-dimensional, so it's like kind of.
Super repulsive.
It has a repulsive. It would maybe appear something similar from a repulsive core, yes. And so now, like coming back to this three-body story, like yes.
Do you have a sense of why is it asymmetric? Like if I think of it just like eating away at the center position, shouldn't I expect those two bumps to be symmetric?
Yes, I mean this has to do with the specifics. There are two things that are not quite symmetric. One is that the binding distance of the macrodimer is smaller than the lattice separation, and the other important factor is that the continuum states, basically the free motional states of having one atom excited in the Rydberg state and one in the ground state, it's kind of like a continuum states of free energy, but they have a lower bound. So unlike in the Fano problem where you have like a flat continuum of states, now you have a lower bounded spectrum and degeneracies. So in combination that leads to this asymmetry. Yes. Okay. I will not go over time. So here, like we have this like a lattice, let's say like a one-dimensional lattice, and the macrodimer can live on these two sides. But it can also live on these two sides, or for that matter, on any other sides. And these configurations are perfectly degenerate. And so now what the light field does, actually, when you go to the strong field, it's not like before that we just excited one of those or this one. The light field can actually induce hoppings between this state and this state. And hoppings is maybe not the best word to describe this process because you get quantum mechanical superpositions of having this state and having this state. So let's look at this, like how it would, this will pan out in spectroscopy. So here's the same spectroscopy signal shown again, but now like I calculate this for 3 atoms instead of just 2, with the entire continuum spectrum included. And the general qualitative features are the same. So you have like this big peak here, then you have 2 side peaks here and there. And now, like for 3 atoms, you see that these 2 peaks actually correspond to quenching the macrodimer in one of the coordinates, but not in the other. So here you have the macrodimer quenched in the first coordinate. Here you have quenched it in the second coordinate, while the other one is wide. And on the right part, where the continuum modes, like again, play a role, there are like some wiggles, but in general, that's the same qualitative behavior. On the other hand, like in the middle, that's the peak where you have cut out these correlations. So the short correlations, the hardcore repulsions effectively, and are left with this. But there's also this very special state on the far left. And that's the state where now the macrodimer is quenched in both directions. So rather than having a macro like kind of quench in only one, you quench in both directions, and it turns out like we can calculate the state, like kind of the wave function of the state in a simple model, and we find that, of course, the center of mass coordinate is just a bystander, but now we get a product state that the entire wave function of this macrodimer triparticle state is described by the center of wave times the relative wave function, the narrow relative wave function of the macrodimer. So it's a 3-particle state that then has like an interesting electronic contribution that's just a product. And here you see it, like the macrodimer could be on the left or it could be on the right, but there are also electronic contributions where you just have one excitation distributed over the 3 atoms. Okay, so from this, like we really like now emerged again, like from two-body interactions, like this very much two-body potential with the light arrived at these what we call macro trimerons, so particles that are bound by light into a 3-particle molecule. Okay, and this is also seen, like kind of this peak here is not really resolved in experiment, but the Simon has made correlation measurements and could show that there's actually an experimental signature of a high likelihood of losing 3 particles on this left edge rather than just 2. Okay, so let me come to the outlook. So like what can we do with this in the long run? So maybe like with better alignment between the macrodimer state and the ground state, can we now look, for example, in the future at higher order correlations where we're not limited to just like 3 particles that are bound, but maybe 4 or 5 particles. What are interactions of these macrodimers? After all, they're in their Rydberg state, so maybe can we get some interesting correlated quantum states on the lattice using these macrodimers? Can we maybe go to higher lattice dimensions rather than just one? Can we look at triangles, triangular lattices, maybe relating to things that Luis Santos told us yesterday about, and can we look at the motion of these macrodimers? Okay, so I'm finished. I just want to reiterate that 3-body interactions emerge from these dipole-dipole interactions in both the Rydberg tweezer arrays and in macrodimers. And if the penguins can somehow regulate their and profit from 3-body interactions, maybe we can too, and look at this. Thank you.
Okay, thank you. Yeah, other questions?
So I would like to ask, so in the first system that you showed us, do you have hopping in the lattice? Does the lattice make any...
There's no atomic motion.
Okay. So everything is within a latticite, these 3 qubits, let's say, or 3 atoms, right?
No, I mean, it's an atomic lattice in the sense that the atoms are fixed, so the atoms don't actually move, but an excitation can hop from one side to the other.
I see, okay.
So that, I mean, that's like, of course, that's very important for the dipole-dipole interactions, right? Like where in general, like you have these hopping terms, and that also makes the 3-body.
And also in the G2 correlation that you showed, why you see always bunching, right? As far as I understood, no anti-bunching at all. Why?
I mean, this is okay. So this means like you fix the central element here. So you say like, if I have lost an atom on side I, what's the probability of also losing an atom on side? And here it's along the diagonal because, like, for technical reasons, these correlations are always lost along the diagonal. So here, like, what's then the probability of losing another atom along the diagonal? So if you had only 2-particle loss, right, then you would have a very positive correlation. If I lose one here, then I also necessarily lose one either here or here. And this is like kind of the generalization to 3 particles. So losing 2, what's the probability of losing another atom in addition to that? So like real 3-particle loss.
Okay, thank you.
Oh, yeah, please.
So you showed this entanglement entropy picture before.
Mm-hmm.
So perhaps you said that and I missed it. So why do you have this point-like picture there?
Yeah, I mean, we don't fully understand that yet. But like maybe like this is something that often happens, like at points where 3 phases meet, there's oftentimes like kind of like a...
Oh, so this is exactly where you
It's not.
triple point there.
It's in the vicinity of that. It's not exactly there, but like probably that is connected to having strong quantum fluctuations there.
Okay, I don't see urgent questions. We have a coffee break now, but before that, we thank you for that nice talk. And, there's a thermal gradient, I guess, to the hot pot of coffee, which is hopefully attractive for some of you.
Sorry.
You said it and I didn't get it. The trees are away. What's the distance between the trees?
In the first part?
Yeah, in the second part.
Oh, in the second part. This is like it's just an optical lattice, actually.
So it's
720 divided by square root 2, so 500 something.
So that's kind of the same length scale of the lattice size.
Right. So like exactly, and it has to be because otherwise the
How
front.
well does that have to be designed?
It doesn't have to be very well designed. So like you have very wide traps, basically 50 nanometer trap width or something across the diagonal. And now you excite to these Rydberg macrodynamos that are maybe like 20 nanometers or so shorter. And this actually makes sure that that reduces the front quantum overlap. So you have weaker lines. So that's what I meant in the end. Like if you had molecules that were just a little wider and thereby better aligned to the trap, you would have larger overlaps and you would see like much more of this effect. So like the dominant reason why we don't see correlations that go beyond 2 is that basically you lose stuff in the continuum of states.
But I guess like here is less about consensus molecular dynamics, it's more of like how the hybridization of these excited states kind of modifies the ground statement.
Basically, assuming that they are produced at the ground state.
I mean, you can pick each of the you can pick that, and in these experiments they were in the ground state. And Simon did the experiment, so he like can probably tell you everything. But like the experiments here are on just the lowest vibrational line.
The coupling is much stronger actually than the basic things we could expect to see large excitations. So long chains of atoms being bound. The reason why we don't see them is that the spatial overlap with the ground state gets exponentially smaller the longer the chain. Because per you basically have one Frank quantum factor. The motional state overlap from the ground state, they feel the vibration in the molecule. You give a long chain, then you get for each pair contributing to that. So they are present, but weaker coupled. That's the reason why two particles, the strongest free particle, still be lost, but already weaker. You have few measurements also showing one more correlations, but nothing beyond.
So the experimental results are this 2019 paper.
It's
That's like new stuff.
really on the archive, I guess, this summer.
So I have a question. So when you go to Rydberg dressing, you typically consider just two, is the blockade from, the Rydberg potential, the soft core potential, is the hard core is because you are blockading the atom and it's just the different, you understand, you know what I mean? The soft core, this only considers two-body interactions,
Exactly, yes.
But as soon as the tuning gets closer, then you have to consider 3 and higher body interactions. So do you think that is similar somehow with these higher order interactions that you were thinking at the beginning?
So in the Rydberg dressing, we would actually consider. I'm not sure.
So because this is something that we are trying to understand. I don't know. So because Nadam Kaufman, when he wants to create the spin squeezing, he has to go fast because otherwise things are bad. And the only way that he can do fast is by operating closer to resonance. But then the Rydberg dressing picture breaks down, and we need to include higher order interactions, 2 body, 3 body, 4 body.
So like 3-4 body interactions actually like on what level?
That's great because it's a thematic elimination of the, I think it's related to what you are saying, but I just wanted to confirm. you have the ground state atom, you have one excited atom, and you're driving the excited atoms with the Ripper. Yes, but you are eliminating so what you are doing at some point is you are eliminating you are generating a dress state.
So this is what you would do in dressing?
In dressing, exactly. But if the point is that the dressing can also go to a regime where, when you are going a little bit closer to resonance.
So like on the lower line transition. So you have a 2-photon transition to the Ripper state?
One for he's alkaline atom, so he has a transition between the 3p0 and the Ripper atom. But the Ripper dressing is closer to resonance.
Okay, so to this intermediate state.
To the intermediate state, to the Ripper state.
Then you can't eliminate the intermediate state?
No, there is no intermediate state.
Oh, sorry.
So you have the ground state, this is 1 and 0, then you have the 3p0, and then you have the Ripper state. And you dress between the 3p0 and the Ripper state. But the Ripper state is adiabatically eliminated, and you have just the 3p0 state, but a little bit of population of the excited state. And then if you look at the interaction of these two atoms, and it satisfies the Ripper dressing potential. But this is only for two particles. This Ripper dressing potential that is a soft form is just a two-body interaction. But we are having to include 3 and 4-body interaction because Adam is closer to resonance. So I wonder if you have thought about that when you do these higher order, when you were trying to complete the higher order van der Waals interactions.
Yeah, I basically put myself right in the Rydberg state, like the Rydberg NS state, and then consider all these virtual hoppings in the Rydberg manifold.
Yes.
So this entire
Have you written that? So do you have this? Is this a simple analytic way to do all these intermediate states?
I just use one flag theory to basically eliminate the far, to systematically go order by order in the perturbation.
Okay, so you do it with a program because that's the part that we are struggling. We don't get an easy analytic formula. Do you get an analytic when you get this? You get an analytic formula for the 4-body interaction?
Yeah, on a simple, you can, yes, not in the dressing one, but in the, just for the interactions, yes, at least in the simple model, if you have, you can always write a general formula.
The formula is there, but
it's there, but I evaluated here for a simple model to just prove this point. I haven't evaluated for a realistic, then I resort to numerics. But maybe I didn't. I'm not sure. Maybe I can it would be nice to I would like to understand the story. Thank you.
You think of the repulsive, is actually you have it also in this kind of diamonds that I was saying, because this somehow is like the contrary effect of having a diamond. For the same reason that you cannot separate the diamonds, you cannot put them together. The same value. So actually what this leads is to a model in which you have a sort of super repulsion. So it's like when you have things like a touch gas and this sort of stuff. Yes. So because now these particles can interpenetrate each other.
So we are thinking about we have n particles or a certain density on the line.
Yes, so basically now these particles are now having each other. Yes, these excitations. And they cannot interpenetrate each other because they cannot approach to a nearest neighbor. So they cannot swap positions or whatever. And now they form this kind of one-dimensional system, which is like representing each other very, very strong. So for example, if you initiate this type of the density wave from 1, 0, it remains there.
Right, exactly. Except for the super exchange.
Here there is no way that there is super exchange. Right? Because there is no possibility that you are going to exchange. Because you cannot enter into the diamond. And therefore there is no way that
so the intermediate state is like super fragment.
You cannot have super exchange. Yes. Like a super repulsion system.
But I was thinking yesterday you mentioned like how you map this basically of having these particles and then you map it onto their center of mass. Like instead of thinking of having two particles, let's think of like kind of they just go to the center of mass and the center of mass. Like is that then a simple model? Right? Like, then it's like kind of just hardcore bosons basically.
It's like a simple. You want to assume that they are like a you can make a diagram. It's like a hardcore boson. Now the problem in one dimension there is no problem. Two dimensions.
Exactly. That's
two dimensions is a different thing. In one two dimensions you can unravel one. Basically you can have these two together. You can pass one into here and then you have three together. Because now they have three V. So you have two. You have one V, one V. You just have to count the number of vehicles. Some things like past two. You still have two dimensions. This one goes along.
okay. Well, that cannot happen.
This cannot happen in one dimension, but this can happen.
It cannot really happen with macro dimensions. Because you have like kind of this molecular state. There's no resonance for one atom that just leaves.
Exactly. This is different.
It's different.
Because in this case, this makes it even more robust to the dimension. But if I create a diamond gas in one dimension, for the reason that they cannot approach two dimensions, they just are stable.
Like also like for 2 dimensions you can have like interesting lattices, right? Just having a triangle around would make it much more interesting.
In your case, if the diamonds are stable, because as I said, the problem in 2 dimensions is like you can have this thing. If I assume that there is a set of blockade radius that they cannot approach, it's possible because there are in the case of diamond, I am safe. But if these guys can approach, then I can have this total decay.
I think this is something
two guys that they get an elastic challenge when they get a triangle. Like a chemical reaction.
Yeah, exactly. I think that we have to really like understood this.
Very well. This is actually what I wanted to point out. It has very venerable roots because the Irene Polanyi London actual method of constructing potential energy surfaces for the H3 system of 3 hydrogen atoms was done in exactly this way, except that they left out some of the interactions in order to make it kind of tractable. And then this technique was expanded upon in the 1950s and 60s by people like Philkins, who developed the technique of diatomics in molecules. DIM was the acronym. Diatomics in molecules. And there is a lovely review on this by John Kelly, which I will be very happy to send you. Well, this is based apparently on another thing that is the modern version of this. The diatomics in molecules version is closely related to something that was developed by an atomic physicist of the name Moffat in the 1950s. But I'm not familiar with Phil Kunzes and diatomics in molecules. It was the talk of the town when I was doing my PhD in information. It's very closely related areas where presentation is absolutely wonderful, and you should have
I had coffee before and I would probably be shaking if I didn't.
So indeed there is a lot of similar perceptions. I think that you can do it in the student assessment, you should be able to see this kind of like this
Exactly. Like that's exactly. It should just like maybe one thing is that it's like an optical system. So just saying, just theoretically look at itself like any density on the left, and just look at the outsides. But like then in addition, of course, like to make it a bit more realistic, I think like I would be interested to like have this drive. That's why I'm asking this to create and then let it
not something that we really see popping up.
I mean, like just one thing.
All those motion files contributing, so it's hard to get some
Free-body interactions, so for the three atoms in the phase diagram, so I didn't quite get my immediate DMID for this. So is this the quantum?
I mean,
Is this, why did the question is, okay, maybe I mean, precisely ask which model did you time and test? So just the two-state model that you have get out, or something?
right, I can just keep it model with the three-part first. So basically, like we were wondering, maybe you have some no matter where this model now comes from, if I have like this one-dimensional chain, let's say like 2 atoms here, then the next atom, 2 atoms, plaquette, kind of here there are plaquette interactions. So you have a drive and you have plaquette interactions with 3 bodies.
I understand now. So this was 3 bodies. That was many bodies. That was not only 3 atoms.
No, this is like a chain. Okay. So now like kind of a first and I explained everything for the plaquette, but then like it was of course, otherwise that would have just been
exactly. So this is because I was thinking, okay, did I miss anything? Did I miss anything else?
Okay. It could have made sense, right? Because the classical phases are somehow like very much. I mean, they have already given like very good intuition, for which you don't need absolutely no computation. But then there's like the stuff that they haven't really understood. For like 25 atoms. The computation is, I mean, of course, like it's like any system is
yeah, but the question is really what is one looking for? So we're looking at these many more interactions needed to performance, and in the end, I mean, so to do with the classical case diagram, right, they can also go to 2D and look at something nice in transitions into stripes and I don't know what. But then the question is, okay, what interesting things are there when you add
because you like
the transfer is
it's like some sort of entanglement. Entanglement always also like the 2 body interactions, and so like it's actually different to get this from 3 body. Honestly, I don't know. It's more like, can you deal with it? That was like kind of a curiosity towards the thing. But like at the end of the day, like I don't know, like if we will either get like new physics, in terms of phases or something, or if we could use it like like at least for some, let's say like do a gate and three-particle interactions. Can you do like fundamentally new things just because you are a three-body? And that's something I don't know.
super understood. There's this paper with this, the 3 particles can be entangled in 2 different ways that are qualitatively different. Yeah, I think it's Chemisirak, so I don't know, but then we can build a bridge there.
Well, like maybe, I was thinking about like this maximum unitary set. Okay, let's say like you have then always depends on like different sets.
No, indeed.
Like I don't know, like I mentioned
I was also
you can, but like it's like you can, but then like you didn't also immediately.
So, but what I can, so first of all, have you done finite size scaling for the system?
For the first diagram?
Yes.
No, not yet.
Okay.
And these calculations are from that.
Okay, so the other thing is that I didn't understand whether there is an interplay between 2 and 3 bodies. This I can
probably yes, but in the first calculations we just like for 2 bodies.
Okay. Because I would imagine essentially that really there is such an interplay, right?
Yeah. To look at it, at the end of the day, just becomes more complicated. Yeah. It's another question. So I think like our plan now is to just write this up and they kind of just have a this model, and then maybe like if there's interest, like specifically look for something
Yeah, we are trying to do the same actually with the polars now. Yes, but having really distinguishable impurities like a Freck-Born system and try and construct an effective Hamiltonian to see the interplay between 2 and 3 body interactions. And actually even in the mean field level you can see this interplay and you can really maximize 3 particle interactions.
Like a scattering depth or something, or like effective contact?
It's effective contact interaction. Yeah, we don't go to this strongly attractive regime right now. Yeah, but this is in quasi 1D what we do right now, not in 2 or 3D. Yeah, for 2 and 3D it will get. But you know also these papers by Bulgats, so that they have proposed that these 3-body interactions can act similarly to these quantum fluctuations. Okay, could send to say they have seen that instead of using
It's not this kind of typical speculation tips that you have one citation after the other.
It's very much the same. Good talk, by the way. Nice.
Yeah, me too. No one passed.
Also, results from this morning.
Yeah, sort of.
To us all.
Real good intuitive understanding, but I can tell you.
Okay, so you convert from this figure
2 times. Zero momentum state and burst excitations where you need to scatter the photon h by k and another photon h by k. So scattering photons from the power but dressed by presence of photon dressing. You can see logically
what they have to do, right?
by some
They have
simulations give us the right system of nonlinear differential expression.
Right. Like, you know, like forward.
Plays a role. I think, well, we have changed kappa. Numerically, we see that frequency, but I don't have an explanation how. I don't have
I don't
That's just a second. That's a spin up.
So at some point we are going to get some more.
Yes.
This kind of
Yes.
So maybe
Okay, let's start the rest of the session. And I'm not attending top. But before we start, I think there is an extension of the poster session after the end, and I was promised that there are even newer posters too, not just the old ones. So we'll begin with Stefan Ostermann, and he is a co-organizer, so he knows better than anybody else the value of sticking to time.
Okay, now pressure's on me. Yes, I will do my best. Thanks, Hossein, and yeah, of course, thanks to all of you for coming, staying, and discussing, giving great talks. It's been a pleasure so far, and I will also try to contribute now to this series of great talks. And you also already saw some work I was involved in regarding dipole-coupled arrays by Susanne Jelin today. So I decided to talk about something else we've been working on already since 1.5 years now, and it's the first time we sort of present this in a bit larger community, in up to a certain degree of detail. And yeah, I'm curious what you think, and I'm going to walk you through our ideas, which are about doing quantum simulation of, I call it now, strongly correlated molecules and materials using the Rydberg array platform here at Harvard. And in particular, we want to do this in an as hardware efficient way as possible. And before I dive into my talk, I would really like to acknowledge the big number of collaborators on this project. And it was a lot of fun to brainstorm, work out details, and really kind of define sort of this project over the course of the last 1.5 years together with them. And on the PI side, that's Martin Hatt-Gordon at UC Berkeley, who is a hardcore computational quantum chemist. Michel Lukin here at Harvard, and Susanne Jelin, also here at Harvard. And on the postdoc / grad student side, I would like to mention in particular Nishad, who is also in the audience and who did a lot of the heavy lifting on the one hand, but also didn't bother to move to Berkeley for an entire summer, learn chemistry, come back and teach it to us, basically. And we also had like lots of discussions with like other people like James, who is also a chemist, Abigail, Rodrigo, Marcin, and many people with different backgrounds really bringing this thing together to what I will present now, basically. Yeah, according to some, and I think they're getting more, we live in the quantum decade. Meaning that now big and small companies, labs, and new groups are starting to build quantum devices, quantum computers, which are expected to be powerful on the long run and really kind of contribute to our society and our understanding of nature. And of course, the question now is, what do we do with these quantum computers and devices, and what can we apply them to? And if you ask Google or nowadays ChatGPT, there are many terms floating around. Factoring, search algorithms, quantum machine learning, cryptography, financial modeling, optimization problems. For this workshop, all of those are pretty irrelevant, I would say. However, there are two applications, which are the two down here, material science and drug discovery, which pops up quite frequently when one talks about quantum computers. And I think these are very relevant to this workshop in a way, as I will show in the following. And I would like to put them in the bigger realm of quantum chemistry, and that's exactly what today's talk is going to be about. Quantum chemistry, in general, is solving an electronic structure problem of many nuclei and electrons, which interact via Coulomb interaction. And in the Born-Oppenheimer approximation, the electrons also have a kinetic degree of freedom, which lets them move around and form bonds and all complicated things. And in general, this is a very difficult many-body problem one has to solve. And that's basically sort of the problem we'll tackle, even though we will simplify it quite a bit to actually make it hardware efficient, as I mentioned. Because it turns out that, after all, advancing quantum chemistry, or in particular computational quantum chemistry, with those quantum devices which are expected to be very powerful, is actually very hard and challenging. And that's due to two main reasons. The first one is just that classical quantum chemistry and computational methods, real ab initio methods based basically on this Hamiltonian, are very good. So this is an old field which was basically established with the first classical computers almost, like big scale classical computers. And there are very good algorithms to solve these problems for quite large molecules and materials. And the second reason is that the actual hardware requirements one would have to kind of fulfill to really push this field forward with a quantum computation platform, they are really difficult to reach actually, at least in the near term. And to sort of be a bit more quantitative on this, there was a paper recently by the Microsoft quantum sort of team, and they were asking how hard is it actually to solve useful or important problems on those machines. And the first problems they looked into were like complicated quantum dynamics problems. And on the y-axis here, you see the number of qubits they expect to be around. And on the x-axis, it's the runtime it would take to simulate and solve such problems. And it turns out that, for example, factoring, which is this obvious application, already is quite hard, even with quite a large number of qubits with given currently top-notch algorithms. But actually, quantum chemistry is even harder, according to them, that basically even with millions of numbers of qubits, actually some of those problems will take centuries, basically. And such a plot, of course, has to be taken with a grain of salt because lots of improvements can be done here to actually shift these things to the left and down. But just to give you a feeling that it's usually not easy to actually do good quantum chemistry on quantum computers, for example. And that was sort of the starting point of our discussion quite some time ago with this big group of people. The goal was really to advance quantum chemistry and get insights into problems motivated from quantum chemistry in the near term by, on the one hand, using state-of-the-art platforms. And we will in particular focus on programmable Rydberg atom arrays. Also leveraging insights obtained from those very good classical methods. And then focus on well-targeted problems which are good for those near-term devices, which are noisy and not scalable to millions and millions of qubits. And the target problem we will study in the following is a high-spin Heisenberg model with arbitrary connectivity and potential higher-order terms. So what does this mean? We will have spins, but since they are high spins, usually like the spin quantum number will be larger than 1/2, so they're big spins. And they're like on some sort of lattice or in some configurations, and each spin talks to each other in a highly non-trivial way with some connectivity which is established by an interaction matrix. And they can interact in various ways, anisotropic, isotropic, via an SXYC interaction, and also like potential higher orders of spin interactions. And I will come back to these terms like this later. So actually in the very framework of this workshop, what we will do is we will use a long-range interacting platform, these Rydberg atoms, which talk to each other on a long range, to study and simulate an even more long-range model, like all-to-all in principle, or like complicated interacting many-body model on top of that. And as it turns out, actually such high-spin Heisenberg models, they are pretty good models for what the chemists call multi-radicals, which are basically molecules which have lots of free electrons moving around, which are not locked due to some bonding mechanism. If these electrons are localized due to some chemical constraints. And they're usually not that, well, difficult to solve because the Hilbert space scales very badly. but they're quite easy to obtain, like the interactions and the spin size, from ab initio quantum chemistry methods. And on top of that, they have a more natural mapping to the hardware we are considering in this problem. So now you could, of course, say, okay, good. So now we're at the Heisenberg model. We know the Heisenberg model, and how much quantum chemistry is left in there now? And why do we talk about quantum chemistry when we're solving this model? So for this, let me actually take a step back and explain this based on an example molecule, which is this molecule here, which is part of the so-called oxygen evolving complex, which provides electrons to photosynthesis in plants, basically, by splitting water into hydrogen, electrons, and oxygen. And this molecule has 4 manganese atoms, 1, 2, 3, 4, some oxygens, and 1 calcium atom. And if we now look at the periodic table and localize manganese, we see that it's here in the middle, just next to iron of the transition metals in the periodic table. And if we take a closer look at the electron configuration of these manganese atoms, we see that it has 7 valence electrons, so 7 outer shell electrons. And what ab initio quantum chemistry methods now can do, they can calculate the bonding structure of such a molecule, and therefore also determine the so-called oxidation state of these manganese atoms. And these numbers I put here next to these atoms, they tell us in which oxidation state these manganese atoms are. So this number 4 here corresponds to the fact that 4 out of these 7 valence electrons, they're somehow locked up due to bonding with this oxygen in particular, meaning they're gone. But what we're left with are 3 of the valence electrons, which are left, and they form a spin 3 half degree of freedom, and they're usually called the active electrons in the molecule. So basically, the Coulomb interaction between these neighboring atoms and the manganese will localize those electrons. Then the ferromagnetic exchange interactions will make them a big spin 3 half, and super exchange will make them talk to each other, like the different spins. Because also the manganese, maybe to mention, they can be in different oxidation states. So this, in this case, for example, just 3 out of those 4 are taken up. So this will be a spin 2 degree of freedom. And then they talk to each other in a non-trivial way, meaning that we can map this molecule, or not we, but the computational chemists can map such a molecule by using their methods, basically, onto a spin model. And this spin model usually takes the form of an S.S interaction with some interaction matrix, where this S is now the vector Sx, Yc, but for a large spin, so it's not a poly, but it's a larger spin matrix. And in principle, these Hamiltonians will also have higher order terms, and these higher order terms are sort of perturbations on top of this, which take into account first order kinetic degrees of freedom of these electrons, sort of like in the molecule. And of course, such a model now has a Hilbert space scaling, which goes with 2s plus 1 to the n, so not just 2 to the n, like in a spin model, or like a spin 1 half model, but it's sort of even worse because of this s here, which is in general large. And that's sort of the model we want to solve now. So in a sense, going back to this slide here, we want to take these maybe still very simple, the simplest quantum chemistry problems, and translate them from this full electronic structure problem into a quantum dynamics problem on the Rydberg platform. That's sort of the idea now. And based on what I just told you, yeah, is there a question?
Can I ask something? Just 2 questions. So one is these spins don't have to be of the same length, right? You just said, I mean, this depends on this oxidation state.
Exactly.
And then, I don't know whether this makes a lot of sense, but let's say if one talks to the solid state physicist I talk to, they tell me basically spins beyond length 1/2 are classical objects. So, can you respond?
I can respond that if you solve these types of Heisenberg models, like you will couple to many spin sectors, and in principle they will be all correlated.
Okay.
So if you look at an entanglement entropy, it will not be for sure. Like this is like the state, ground states or states. It's usually not a classical state.
Okay.
So mean field does It's true. Actually, like there are like mean field approaches one can do here, and then but for like we are actually in particular. I mean, yes. The point is that we look into models where this Jij is in like some molecules, and that's what the strongly correlated matter in the title basically tells us, where they're exactly not classical. Maybe that's maybe the answer I can give right now. But it's true that actually, like, it's not trivial, like, why this is the case, but there are these molecules which are then hard to solve. Yeah, that's a good point. So, yes, exactly. So now what we need, yes?
If you go back to this Hamiltonian, you said that this is Frank Nies and group, so they map the Hamiltonian for this molecule to this space.
Exactly. So this paper here actually takes exactly this one and does this step. Exactly, yeah.
And can I ask why stop there? Why don't you have higher order terms if you have large spin?
You don't have to stop there, but they, of course, like the contributions get smaller. But in principle, you can have any order. Yes, that's a good point. I mean, I just wrote down the first two, but in general, they're like any orders. And the more orders you include, the more less approximate your Hamiltonian sort of is. Exactly. So what we need now are, on the one hand, obviously, high spins beyond 1/2. We need to establish somehow arbitrary connection between those spins. And then once we have done all this, we also want to have an efficient readout mechanism to actually say something about these molecules or about these state models, which is useful for chemistry applications, for example. And as I will show you during the remainder of my talk, is that this first part we can actually solve by using Rydberg blockade in those systems. This part, the connectivity, we can actually solve by using atom moving, which is a technology which was developed recently on those Rydberg tweezer array platforms in an efficient way. And the last part with the readout, we can actually also realize by doing snapshot measurements, as it's usually done on those platforms, and then post-processing them on a classical computer again. So let's start with this first block, engineering a large spin. For this, we will take, for example, 3 Rydberg atoms in a tweezer array. So they will have this like 3-level structure here. The Sera in the 1 hyperfine level encodes the spin. And then there is a Rydberg state which mediates interactions in a symmetric way among those atoms. And we assume that they're placed within this blockade radius where basically there's a strong nonlinearity, meaning that only one atom at a time can be excited. However, just doing this will not just make them automatically a spin 3/2. What we have to do is we have to restrict them to the symmetric spin subspace such that they actually act as one collective big spin. And this is something we can engineer by basically using a Hamiltonian which is S squared, because the lowest energy state of this Hamiltonian will be the spin n½ state, and any spin flip of one of those qubits here, individual qubits, will kind of increase the energy. So the low energy state is the good one, the one we want to have, the large collective spin, where this S here is this collective spin operator of the individual polys. But now the question is, how do we actually engineer such an Hamiltonian? And for this, we need to find what we call a multi-qubit gate, or like a global drive scheme, which actually realizes such an Hamiltonian. And to do this, we use techniques from optimal control, in particular this GRAPE technique, which stands for gradient ascent pulse engineering, which was originally developed for NMR schemes, but was also recently applied by Guido Popir and collaborators to actually engineer multi-qubit gates on such platforms. And now the mechanism there is basically that we have our atomic Hamiltonian, which has sort of 2 Rabi frequencies here, or 2 pulses, which global drives we can use, and they are time dependent. And on top of these kind of transitions, it also has this Rydberg interaction, strong nonlinearity. And if this one is really strong, that's sort of a dominating term. And everything boils down to optimizing this global drive such that we actually realize a target unitary which kind of realizes such a Hamiltonian evolution in this model. So the mechanism, you chop down your time into frames, and you optimize each time frame to actually end up with this target unitary. And it turns out this is actually possible with very large fidelities to actually realize this unitary. And even for large atom numbers, like 8 here, the pulses we get, they're not crazy. So they're like feasible on the experimental platform as well. And
they get more and more crazy?
They get more and more crazy, and there are like also many different ones with similar fidelities. I mean, it's not like this is one example. We're actually still actively investigating this a little more, but the more important fact here is they exist and the fidelity is good. That's maybe the claim here. The more important thing is that, yes, they exist, and if we look how the gate time, so the time such a pulse has to we have to shine it onto the atoms, scales with a number of qubits in one of those clusters, we see that it scales pretty much linear in the number of spins in one cluster, which is in very stark contrast to a 2-qubit trotterized decomposition of such a unitary, which one would have to implement if one would do this, for example, on a digital quantum computer, which blows up immediately and scales exponentially. And here I would like to mention that this non-exponential scaling with the system size is already the first hint that the hardware you use, this Rydberg platform, is kind of advantageous over other things because it just has this like nice interaction built in a natural way. We're not the very first ones thinking about quantum chemistry on quantum simulators or quantum processors in this like Heisenberg picture way. There's a recent paper by Garnet Chan, who is a quantum chemist at Caltech, and they tried to simulate actually very small, but still molecules with iron, for example, which also has these many active electrons, on the Google Sycamore processor. And if one actually takes a closer look at their paper, there is this one sentence where they say, although those metal atoms or ions have in principle large total spin, exactly due to the reason I just told you, they then finally further simplified the model to reduce the quantum resources necessary and just kept the non-trivial interactions into account, just exactly because of the fact that engineering large spins is very costly. So in a sense, we are able to do this first block, this high spin engineering. Yes.
Cannot you use just reversing and operating the core, so where the interactions are all to all? If you do that and you drive, you get a less square minus a c square Hamiltonian that keep you alive.
I agree, actually. Yeah, maybe that's an alternative way to get a less complicated gate, sort of, or pulse we need. Yes, because it's flat. Yeah,
it's flat,
that's true. That's a good.
The key here, though, is that it's still using the blockade mechanism, so it's still robust to things like motional fluctuations.
That's true. Yeah, but I mean, also the flat tracing has the same thing. Yeah. Yeah.
It also relies on the blockade.
If you like this comes with an all-to-all symmetry intrinsically.
Yes. Mm-hmm. You know, I mean, I agree that in principle, like, pressing could be an alternative. I mean, I guess it will not be that different after all. All we need is the interaction. Actually, the power law of the interaction is not that crucial, actually, here. Yes. but yeah, it's a good point. I mean, it's not what I'm presenting is not the only scheme, as I will also comment later. One could do these things, actually, yeah. So now we have these large spins. We engineered them in those clusters of spin 1/2s. Now we want to have them talk to each other and make them interact. So for this now, consider we have a tweezer array and we place these spin 1/2s in tweezers such that they're within a blockade radius in all those clusters. Now the first step we will do is we will use this intra-cluster gate we just realized or like showed that they exist for different numbers of qubits in a cluster and apply it. So now these will be spin 3/2, spin 2, spin 1, and different spins. Now the idea is to use this atom moving, which is very efficient on those platforms, and reconfigure this entire array, and apply an intercluster gate, which now entangles basically these qubits in a way how we kind of want it, based on our interaction matrix. So these sigmas now are the like single qubit operators, and again we can use this great scheme to actually come up with a global drive sequence which does exactly such a Hamiltonian. Then we go back and reconfigure the entire system, and then we just repeat this process many, many times. And actually one can show if one does this like in a trotterized way, having these clusters, like the cluster pulses I just showed you on this like 3-level system,
including with these 2 qubit interactions on average, to leading order, this realizes this target Hamiltonian like with a large spin now, given a given interaction matrix on average, for certain particular times in which each of those clusters, each of these pulses is basically applied. So this is nice. So we are actually able to realize this one. And actually you can do it better, because I told you there are these higher order terms which are relevant for quantum chemistry.
Sorry, are you
yes.
limited just to move into the neighbors?
No.
You can't really move all around.
In principle, exactly. The point is like this is a very high fidelity application. Actually, you don't lose a lot during this. So you can, for example, here you see like this one talks to this cluster. So this is a beyond nearest neighbor. And in principle, you could even move it here. So you can, I mean, this is one example we picked for artistic reasons, I would say. But in principle, you can do many different things, yes.
What's the typical time scale for doing that?
Oh, now the time scale here is like it's short. It takes time. I don't know exactly, but it's like on the order of. It's not fast, so it's on the order of seconds, I guess, right? Microseconds. Okay, yeah. So yeah, I mean, it's not actually we're not competing on times here. It's more about competing on Hilbert space size we can implement. Maybe that's maybe the point to put it.
Yeah, but on this planet, time rules.
That's true. Yes. So yeah, we have these moving steps in between which take time, but
the fidelity is like the error is like
exactly.
-5.
Yes. So you don't make an error by doing this. So you can take the time. So there's no decoherence if that was your question. Or almost no decoherence. Yeah. Yeah, exactly. So now the nice thing is that if we do some Floquet engineering and basically writing down the different orders which appear in such a pulse sequence of applied unitaries, one can actually sort of engineer a mistake to a symmetrist, not a mistake, but target this pulse sequence, which now is symmetrized in a way to kind of take into account higher order terms. And then one kind of plays around with like these interactions. So the blue one is always the interaction Hamiltonian. So this one, how long this one is applied, and one tunes these parameters A and B. Actually, one realizes that like with these higher order terms, there is quite some range of coefficients, J1, J2, J3. Now just for 2 spins, one can actually access by doing this optimization. So in a sense, by making the Floquet picture a little worse, one kind of mixes up higher order terms, which don't cancel now. But that's good for us because we want them. So we can actually tune it by kind of destroying our pulse sequence a little bit. So this kind of higher order term engineering is like naturally built into this system in a way. So, yeah.
Can you comment, like, it seems like the way that you do the interactions don't necessarily preserve the large spin structure, but it seems like all the terms that you get preserve that spin structure. Can you
no.
tell us a little bit?
Yeah, no, that's true. So the interactions, they can flip spins, and then you leave this this kind of large spin, and that's sort of exactly what is, so the range of values we have plotted here is exactly this part where this doesn't happen, basically. So the white region there, we would actually have exactly this process going. Exactly. So now we have established the connectivity. Now the question is, what do we do now in terms of reading out states and properties of this model, which is the last big ingredient we need. And for this, we will use just the evolution scheme I told you by applying this time evolution, and do this for different times and take snapshots of all the spins, basically. And then we want to translate this into material properties. And the fundamental scheme now is that we will use one like ancilla style qubit. So we will have one qubit, not a large spin. And this large qubit serves as our sort of reference in a way. And we will apply a controlled perturbation now on our system. And the nice thing is that this controlled perturbation R now will establish in general a finite overlap with the low energy states, not just the ground state, with the whole low energy spectrum of our Hilbert space. And then the snapshots after this process here in different bases basically contain a lot of information about actually what was happening in this black box originally. And the nice thing is that the Heisenberg Hamiltonian I just told you about, it's U1 symmetric. So this all up state, which is easy to prepare according to the experimentalists,
is sort of always our reference energy. And the core of the protocol are then correlation functions, which is the main thing one extracts from snapshots by taking many and kind of establishing correlators. And by measuring the system always in the x basis and the ancillas in the x and y basis, what one figures out is that actually like those measurements just in the x basis give us exactly access to all sorts of correlation functions. And they can be determined for any polystring x then, where a tensor product of different polys. And since this is like a complete basis, basically in general, if we can gather all those correlations, we know everything what's going on here, because all the information about this time evolution after this perturbation was applied to the all-up state is actually encoded in those correlators. So the spectroscopy procedure then would be basically the following. We aggregate all those correlation functions for different operators O. We Fourier transform them, sum them up, and then average, and that's important, over many perturbations R here. And this, in principle, will give us a spectral density, basically. So the dashed lines here are the ED results one would get. And then after doing like a certain number of samples over different Rs, what one gets will be like peaks like this. And already looking at this picture, we see that there are colors, and it's not just like one global spectral density, because basically by putting projectors on top of these X polys here into this correlator, in a sense, one can project each spin sector down, each state down into the spin sector it lives in. So we get a kind of spin resolved density of states. But already we also see here that there are two main limitations for this system, which is that these peaks have a certain width. And this width, maybe that's like a little bit coming back to Andreas' discussion, they are like, the limit here is the coherence time in the system and how decoherence processes kick in. So they set our resolution in the spectral space because they limit the time we can actually apply this sequence. And the second big limitation is that this R operator, it has to result in an overlap with low energy states. And that's not always necessarily the case, so we have to maybe sample too many of those R's to actually make it scalable. But the nice thing is that this random global perturbation I just told you, which is a random rotation on all the individual spins, can be improved basically by finding a little bit a better state for the Hamiltonian we actually want to solve. And for example, we can find a mean field solution, which actually can then be implemented by having like a series of single qubit gates, controlled single qubit gates. And if we want to like even go a bit further and want to kind of have a little bit of quantumness in our state, for example, one can have like a very low bond dimension MPS state we can get from the MRG, and there are like mechanisms to translate those into a series of controlled two qubit gates. And these gates are actually native, and as it was shown in a recent paper, on the platform available. So such schemes are not that hard in a sense, meaning that we can basically get a better R, which enhances the ground state overlap for reasonably chain lengths significantly compared to the random case. So the bond dimension 2 state is already up here, whereas the random is basically all the way down. So we need to sample over way less perturbations to get much more information out, basically. That's the idea here. And the nice thing about this insight is also that the approach I just showed you can actually be combined with other state-of-the-art methods which are available. And the big trick we have is that we now can actually do full time evolution after we do approximate available methods here in the beginning. Let's now see how this actually like scales up to a little larger molecules. And for this, I would like to go back to the original OEC complex I showed in the very beginning. And this molecule is already big enough that the spectrum looks pretty messy, but still it's small enough that we can kind of do exact diagonalization in our laptop, meaning that these dashed lines, we know exactly what sort of energies the low energy sector has. And we see that this kind of total spectrum for,
Do you do that by solving a spin model? Or?
Yes,
Yeah.
exactly. That's solving the spin model, basically. And then we simulate this whole process I showed you for random Rs and like collecting these correlators. And that's this black curve one then gets. And we see that this black curve has peaks in the right places, and it already captures kind of the spectrum quite well. However, the problem is like if we zoom into this low energy spectrum, our
Fourier limit, let's say, in the spectral resolution is given by how wide those peaks are and how long we can simulate. But here, the fact that actually we have this projection onto the different energy sectors of states allows us actually to go to even resolve very tiny energy differences if the two neighboring states have different spin, basically. So that's another feature of this kind of spin-resolved spectroscopy. And the second thing the spin-resolved spectroscopy allows us to do is really like get to something the quantum chemists call the spin ladder, basically like out of the low energy spectrum, what sort of spin sector all those individual states live in. And here maybe it comes back to this kind of, is it classical or not? I mean, they cover like many different spin sectors. So that's the kind of feature of strongly correlated systems. And the reason this is interesting is because actually, like, while the classical quantum chemistry simulations are good, sometimes it's not that clear like what the exact structure of the molecule is. And the model Hamiltonians that then derive are actually quite different sometimes and result in very different spin ladders. So for larger systems, one could, of course, then say we can solve them and then compare it to, for example, experiments and say this is the good model Hamiltonian for a given molecule, for example. So now, yeah, we established this entire framework by engineering large spins on a Rydberg platform, making them talk with each other, and also have very efficient readout. So the full pipeline I would like to summarize, and Hossein said I should not go over time, so I haven't do that. We sort of came up with, I think, a rather realistic, maybe not tomorrow, but near-term platform and scheme to really achieve sort of useful insight into problems inspired by quantum chemistry and material science by taking some sort of strongly correlated matter. And while I now picked this kind of molecule, it can also be other things like these Kitaev materials or complicated condensed matter systems involving large spins. We mapped them to a model spin Hamiltonian, which is based on a large spin Heisenberg model in our case, which we then implement on the Rydberg array. We evolve for a certain time. We have a way to kind of have Foucault time engineering, like time evolution in the system. And then we actually can do spectroscopy. So we are not only interested in the low energy states, now we are actually interested in the entire low energy spectrum, which is usually hard with other classical methods available, because they govern, for example, susceptibilities and things which are relevant for applications of chemistry. And this brings me to an outlook of this whole thing. So while this is now, I think, a first approach we took, and I think it looks promising, there are many open questions, and I think there are many avenues to cover. One of them is the question of scalability. I already told you there is this problem of sample complexity. How many R's do we need for a certain large system? So we want to optimize this perturbation R basically on the long run. Maybe there are alternative ways to actually prepare good initial states, like adiabatic state preparation. Maybe one can combine it with other approaches on a more digital side, like variational quantum eigencircuits. Also understand what is the role of noise, which will be more important once we scale systems up to large system sizes. For the experimental part, the gates we get, they exist and they're not crazy, but I think one can actually, if one really sits down, optimize them more. And that's what we're actually doing a little bit at the moment. But also, like, coming back to this workshop, the thing is that while this platform was very native for us in a sense, I think there can be alternative platforms which can answer similar questions in a different way. I mean, cavities, we saw basically cavities can engineer interactions. Waveguides can do the same. We might not need clusters to engineer spins. Also qubits, like internal structures of internal degrees of freedoms of atoms, can do a similar job with other caveats, but in general it's possible. And even the Heisenberg model I showed you in the beginning and the one we implemented here only describes, one has to be fair here, a very small portion of quantum chemistry. But there are ways to actually implement more general model Hamiltonians, we believe, and also like ways to actually then at some point go to fermionic Hamiltonians, and I'm excited to discuss. And yeah, with this, I think I'm at the end, and I want to thank all the collaborators again, and thank you for listening. Thanks.
Stefan's management of time will get better as he organizes more conferences.
It's time for a couple of questions.
Yeah, Valentin.
Also, in the beginning, you talked about this, or you showed us this very general chemistry.
Is it on? I can't.
just this very general
chemistry Hamiltonian that included the kinetic energy. So like now in your in the spin model that you derived, there was no kinetic energy. So can you say a bit more, like in what types of systems the kinetic energy term doesn't matter and when it matters, and because that's something that probably cannot be covered by this current approach, right?
No, I mean it's perturbatively covered by these higher order terms, but in general no. And actually, like for example, this, so that the extension you're sort of asking for in next order would be this thing called the TJ model, which is sort of our model adding a kinetic degree of freedom. But it's correct, there's no kinetic degree of freedom in the model. And the models where this usually is good, for example, if you go back to this one, and that's now just quoting quantum chemists, basically, if you have, for example, oxygen blocking those transition metals, oxygen is very hard to polarize, meaning that usually it's sort of insulating sort of those individual atoms. And also, for example, similar things happen in those big single molecular magnets where you have iron atoms which are shielded by the surrounding atoms, which are not polarizable in a sense. And then all the interaction is sort of super exchange interactions and no kinetic degree of freedom. And that's the subclass of materials / molecules we can capture here, which is a small subclass, yes. But yeah.
And those are known to like have strong quantum effects. Okay.
Exactly.
Okay. Yep. Thank you.
Other questions?
Yeah, maybe related to Valentin's question. So suppose we introduce this hopping of the electron and solve the molecular orbit first, and then have this second quantized Hamiltonian. Is that possible to group the molecular orbitals into a large spin model and then use the same trick to solve for other chemical problems?
I think, I mean, it's not the same approach, but I think the approach is one can extend it to these problems. Yes, that would be my fast answer. But yeah, I think that's actually really the very important next step before one really wants to push things. Yeah, really starting with the second quantized kinetic degree of freedom and then implementing it on top, sort of. Yeah.
Thank you.
Okay, thank you. In the interest of time, I guess join me in thanking Stefan.
Yeah.
So,
microphone. Yes, and you want this one? That's fine.
we'll move to the next talk by Roland Krotze from Stanford, whose name was butchered on the abstract page. My apologies.
Only the last name.
Only the last name.
Yes.
But I think on the program itself is
here it's
correct.
Yeah. Okay. Cool.
Okay. So
you'll give me a warning. Yes. Okay. Great. Yes. Thank you for the introduction and for the platform to talk about some of our very recent results. So I'm going to be talking about replica symmetry breaking in a cavity platform. And so this is work done in the group of Professor Benjamin Lev at Stanford. So to set the stage for this replica symmetry breaking, this is a concept in the context of spin glasses. So let me start by defining and introducing these systems. So the energetic description of these systems is very straightforward. We just need an Ising Hamiltonian. So with pairwise interactions. But the crucial key is that the J-I-J interactions strengths have disorder, and not only in their magnitude, but also their sign. So some interactions will be ferromagnetic and some will be anti-ferromagnetic. And it turns out that doing this for large-scale systems actually shows all kinds of interesting complex behavior that basically emerges out of this simple Hamiltonian. And for example, the finding the ground state of these systems is computationally equivalent to solving many of these real-world quadratic optimization problems. And they all belong to a class of NP-hard problems. Now, fundamentally, the reason why this is so hard has to do with the concept of frustration. So here it's illustrated the geometric frustration a triangle of spins that can point up or down. And the bonds here are, these two bonds are ferromagnetic and this one is anti-ferromagnetic. You can simply see you cannot satisfy all bonds at the same time. Now for this simple system, small system, we can enumerate all states, but once this grows to a very large system, the energy landscape becomes very complex. And this, try to illustrate here in the bottom left, of course the Hilbert space is high dimensional, but it has lots of local minima. And so here it's actually a little bit tricky to figure out which of these local minima is the ground state. And so that's basically what a spin glass is, but our understanding of it and describing it beyond this simple definition is actually quite tricky. And so Giorgio Parisi won the Nobel Prize a couple years ago for describing sort of the structure that these local minima have in a particular version of the spin glass, all-to-all infinite range. So that's where the stage is set. So let me go a little bit beyond the definition and tell you about how you can recognize a spin glass, what sets it apart. So for this, I take this canonical example of a Sherrington-Kirkpatrick model. It's the same Hamiltonian, it's just a particular name for the ensemble of J matrices. So they're sampled from a normal distribution with a controlled mean and variance scaled such that the thermodynamic limit made sense. And for this one, the phase diagram is known. So when the temperature is high, we have a paramagnetic phase. When the mean dominates, this is just a ferromagnet. But then when the variance is the dominant term of the Hamiltonian, then you get a spin glass phase. And so to tell this spin glass phase apart, we need an order parameter to describe it. So we know that the ferromagnet is described typically by magnetization. And for the spin glass phase, you can use something called the replica overlap. So here I just give the definitions. The magnetization is, as you know, just the sum over all spins. But for replica overlap, we have to think a little bit more. So the basic idea is we take two systems that have the same quench disorder and observe them. And you'll find that those systems will get stuck in different local minima in this energy landscape. So if we look at the instantaneous state, you'll find that two replicas can have different states. And so this overlap between the states you find is not one, basically. So with these two order parameters, we can then fill in this phase diagram. And to illustrate, this relates to the concept of non-ergodicity. So you explore, you really get stuck in these local minima. So just to give you a bit of intuition, for a ferromagnet, you can of course still calculate the overlap parameter because the states you'll find are either all up or all down. If I take two copies of the system, if I find in one system all up and the other also, the overlap is 1, or -1 if I find the Z2 symmetric state. Now, instead, if I look at a glassy instance, you can see that in addition to these two peaks that you will basically always have, you'll also find peaks in the interior. So this is an example for a disorder instance that admitted two minima in the energy landscape. But the two minima are basically uncorrelated with each other, so they have practically zero overlap. And if we do this for another disorder instance, you get some other peaks. And so the sensible question here then is to ask, what is this if we average over all the disorder instances? And then you can see you get a smooth filling in of this overlap distribution with a sort of known curve. And so that's the key feature of a spin glass, and this is what's called replica symmetry breaking. So in this talk, I will tell you about how we study this on an experimental platform where we use a multi-mode confocal cavity. So I'll introduce that and then tell you about two very new results. One in theory, where we study the dynamics near the phase transition of this system, and then experimentally how we realize a vector version of the spin glass. So as I said, we use neutral atoms inside optical cavities. And we use this transverse pumping phase transition. So we shine laser light transversely to the atoms. Initially, they are in a BEC with a homogeneous density, more up to finite size effects. And then, once the superradiant phase transition is reached, atoms scatter some of this pump light into the cavity, and the cavity light makes this optical potential that encourages the development of a density wave of the BEC. And so this has been discussed already a couple times this conference. You can observe this by looking at the light that comes out of the cavity. You'll see that there is a critical pump power for this transverse pump to really reach this threshold. Simultaneously, you can look at the atomic density distribution in time of flight and see the structure of this BEC. And so to understand this phase transition, there is a competition of energies. So normally creating this density wave costs kinetic energy. But this kinetic energy is overcome by the photon-mediated interaction between atoms. So atoms can interact with each other as mediated by the cavity. So that works and can be done in single-mode cavities. Now what we have pioneered in our group is multi-mode cavities. And so having multiple field modes that participate in this physics really brings complexity. And so here I show you an example, or this is transmission spectroscopy of our cavity, which we can tune in situ between multi-mode and single mode and really adjust the sort of photon-mediated interactions and thereby control the connectivity also. And so in addition to then looking at the time information of the light that leaks out of the cavity, we can also look at the spatial information that leaks out. And so we can do holographic techniques to fully reconstruct the electric field inside the cavity, so both the amplitude and the phase. And this will also tell us something about the phase of these density waves and the condensates within. So this is a picture of what that looked like before we installed a lot more optics. This is our cavity. It's about 1 centimeter in length inside a vacuum chamber where we can make ultra-cold gases, BECs of rubidium-87. So I should tell you what this multi-mode cavity does for you in detail, and we have a whole body of work on that. So to do that, we can start by thinking about ray tracing. What if I have an atom inside the cavity? What happens as it emits light? So this light can propagate through the cavity, and as we let the animation finish, we can see a particular pattern emerge. So wherever there is light, there is interactions, because this is a photon-mediated interaction. And so we can recognize that where the atom emitted light, the interaction is strong because the light is focused there. That leads to this local interaction term. There is another spot here across the cavity that also has a strong focus of light that leads to the mirror term, and I'll explain how these two diagonal arms then lead to this other interaction. Now this ray tracing picture can be understood from realizing that the particular cavity we use is a confocal cavity, where the length is equal to the radius of curvature. And a curved mirror with a radius of curvature r has a focal length of r over 2. So propagating from the midplane to the cavity mirror is exactly propagating by the focal distance. So the cavity, as you propagate from the middle to the mirror and get reflected, does a Fourier transform. And you can then see that these two terms, local plus mirror, if you take the Fourier transform of them, you get this kind of cosine interaction. Now, this was a simple ray tracing animation. If we go to actually the Gaussian picture of light and we calculate the electric field, you can see that these two crossing arms interfere and give a light field that has an oscillatory pattern. And so again, that's why you get this cosine interaction. Now, and so this we can all see, as I said, by imaging the light that comes out of the cavity. So we can recognize the two spots, and here in the background, you can see that there is, on the screen a little bit faint, but a non-local field. And so we've previously characterized this interaction, that this interaction length scale C can be really short, of the scale of 2 microns. This sets both the interaction range and the resolution for sort of imaging what is happening inside the cavity. So this is, in a sense, a quantum gas microscope, but in an active one. The light both reveals the information as well as mediates the interactions. And as a side note, then the interaction strengths, characterized by the cooperativity, which in the single mode configuration for us is 5, get boosted by this multi-mode interference. Now, this non-local interaction is interesting because it's sign changing in nature. This cosine can be both positive and negative. And so that's exactly what we can then use to study spin glass physics, where we need this order in the signs. And it's also, in a way, programmable because we can control it by the position of atoms inside the cavity, which we can control with optical tweezers. The other ingredient we need to really study spin glasses is a spin degree of freedom. This can be done by coupling two internal states of the rubidium atom. And after eliminating the cavity field, you find that this realizes an effective Ising model, a transverse field Ising model, where this Jij is exactly set by this non-local interaction. So this is then the ingredients for simulating spin glasses. So here is a rendering of what that could look like. The green spots here are the atoms we put inside the cavity. We use a transverse pump, and the light that leaks out of the cavity here in blue is collected in this interference measurement that reveals us the information about what's going on inside the cavity. So just thinking about this Jij matrix, instead of this is not drawn from a normal distribution, but we've also previously studied and shown that there is both a ferromagnetic phase as well as a spin glass phase and some phase in between that you can see in addition to the paramagnet. So that's just statics. Now I want to say something about the dynamics, because the cavity is inherently an open quantum system. Light that bounces around will leak out. And so this is then sort of sets the stage for driven dissipative dynamics. As I mentioned, there is the superradiant phase transition. So when the spins start in the down state, which is the lowest energy state without the Ising interaction, as we ramp up the transverse pump, they organize into the X bases, either left or right. So far above the superradiant phase transition, we've previously shown that there's already interesting dynamics here that happens due to the dissipation. So the cavity can realize steepest descent dynamics through this spin energy landscape, where it flips the spin that gains the most energy. That's far above the threshold, and now I want to think about what happens near that phase transition, because this is where quantum fluctuations of the cavity fields really play an important role. So then you can ask, what are the effective dynamics of the system as we go through this phase transition? And what's the role of entanglement there? So this we now have approached with numerical simulations of reasonably sized, small but reasonably sized systems. So this is an example of a 15-node graph that we can implement in our cavity. And I'll tell you now about what those some answers to these questions. So to efficiently simulate that, we have to do a little bit of math first. So the system is described by a multi-mode Dicke model, where each cavity field mode is described by a bosonic operator. The spins are described by SZ terms, and then there is an interaction between the spins and the cavity field with a strength G. Now, because we have many modes, we definitely don't want to keep track of all these bosonic fields. So we can try to eliminate them and get to an atom-only description. Now, because the dissipation happens only in the cavity field, we have to be a bit careful not to throw out all the interesting dissipative dynamics as well. So we do this via generalization of this paper that shows that you can retain the interesting dynamics. We end up with an atom-only master equation with collapse operators that act collectively on all spins at the same time. And also those collapse operators have slightly non-Hermitian character due to the dissipation. Then we can unravel this master equation and really look at the evolution of quantum states. And here I show you an example of one of these trajectories. So in the bottom here is the pump schedule. We turn up this transverse pump and take it through the superradiant phase transition. At the same time, we ramp down this field term. It turns out having this be 0 at the end is a bit nicer for making the dynamics converge. So looking at only the x component, we can see in the normal phase, when the spin is still on the south pole, you don't get any average x component. But then as you ramp into the superradiant phase transition, the spins pick up an x, either plus or minus 1. And here you can see an example of some spins decided to still flip their pointing along x. So this is visually a bit better represented on a Bloch sphere, where we can see that the effective dynamics starts all the spins on the south pole, then goes into the interior of the Bloch sphere and pops out to the sides. This is in stark contrast with semi-classical dynamics, which just run around circles here and stay on the surface of the Bloch sphere. So the fact that this quantum state went to the interior of the Bloch sphere implies that there is entanglement that arose as we went through this phase transition. So because we have access to the full quantum state as we did this trajectory, we can also calculate the entanglement entropy. So here we show the entanglement entropy between each individual spin and the rest of the system, and see that as we go through the phase transition, this picks up. And then at later times, there is a revival here that has to do with the spin flip that we saw earlier. So this is a single trajectory. To see that this is robust, we can repeat this for various noise instances and average it and see that, yes, indeed, the entropy remains no matter how sort of the particular trajectory the system took. So next so there is entanglement, then we can ask what does this mean for the dynamics of the system, for example, in terms of energetics. So to set the stage there, I show here the instantaneous, or the expectation value of the energy compared to the instantaneous ground state. And here I show again the semi-classical dynamics. This shaded region shows a region where entanglement is required. And so because this is semi-classical, you cannot enter into this barrier, and the dynamics necessarily ends up at high energy. If I now show this for the quantum trajectories, I really have to zoom in to the bottom here, where the scale is much smaller, and these quantum trajectories, by having this entanglement, can tunnel through this barrier and remain at low energies. And then at long timescales, as we saw in the previous slides, the dissipation actually projects you out into an Ising state. So in the middle of the trajectory here, as we were going through the phase transition, you're entangled, but you end up with a pure state. So the entanglement here plays an important role in remaining in the low energy states of these spin glasses. And ultimately, we find the eigenstate. Now we can ask, if we do this for different noise realizations, we have a whole ensemble of states. What are the properties of this ensemble of states? Do they, for example, have some overlap distribution that is non-trivial? So to do that, we look at an ensemble of 200 trajectories which form our replicas. We can take pairwise overlaps and look at the distribution. So at early times, because the spins are still on the south pole, you basically get random answers, and random answers are orthogonal. We find an overlap that is basically 0. But then as the system evolves and goes through this phase transition and ultimately stabilizes at long times, we find an overlap distribution that has the two posts at plus and minus 1, but also features in the middle. Now, to understand these features, this was for a 15-clump system, we can still enumerate all the states and look at the local minima. And we can find that this system had 6 local minima. 3 of them here in orange have very low energy, and the other 3 have higher energy. And so we can see that if from the 200 trajectories we found, about 50% were in this first local minimum, which is the ground state. The other trajectories mostly were in the local minimas 2 and 3. And so if we then think about if I have 2 replicas and drawing from local minima 1, 2, and 3, you can then see that if you draw this, the first replica finds local minimum 1, the other local minimum 2, we get this peak because we can simply calculate the overlap of those two states. So we can identify then each of the peaks here with the local minima that we know the energy structure, energy landscape has. Of course, we can also compare this to a Monte Carlo simulation at finite temperature, and we find that the best match temperature is about 10% of the spin glass transition temperature, so this is a cold system. But you can also see that this Monte Carlo distribution in red here doesn't match precisely all the details of the ensemble of states we found. So this hints at the ensemble being a non-thermal distribution. Of course, this is not entirely surprising. We have this complicated system with driven dissipative dynamics. It's not a given you're going to find a perfect thermal distribution. So in addition to this overlap distribution, I also want to flash quickly the matrix of distances between individual replicas, where you can really see, as function of time, also a structure emerge. And I didn't really have time to discuss this, but the structure of local minima in spin glasses has a very particular tree-like structure. And this is called ultrametricity. And these matrices that are sort of this block-like structure is very reminiscent of that. So this, as far as I've shown now, was all for a single disorder instance J. So now we can repeat this for different disorder instances. So for different disorder instances, we will find different overlap distributions. And then, as we repeat this enough, if we take an average over disorder instances, we find that the system really shows this Parisi-like distribution with the goalposts and smoothly filled in interior. So again, we can compare this to a finite temperature Monte Carlo. The best fit temperature is pretty much the same. Again, we see that the red lines don't fully match the found ensemble, and again, this shows that it's a non-thermal distribution. Now, as you might remember, the spin glass phase was set apart by having non-zero overlap, but zero magnetization. So for completeness, I shall also show you the magnetization, and this is centered around 0. This is, again, showing in red the thermal ensemble, what you would expect for the system. The width of this distribution would shrink as you make the system larger and larger. So this was for 15 spins. So what I've shown you now is that we can really see this replica symmetry breaking in this driven dissipative system, that entanglement as you go through this phase transition, the superradiant phase transition, helps you find low energy states, that dissipation lets this replica symmetry breaking emerge as you follow the dynamics, and that we find a Parisi-like distribution. So that was all theory and numerical simulations. Now we want to switch to the experiment. So in the experiment, we don't exactly realize this Ising spin glass. Instead, we don't use this internal degree of freedom, but we go back to the picture of density waves. So each BEC now, each clump of atoms can form a density wave. And in a confocal cavity, this density wave actually can be at various locations along the cavity. So this really can pick any location that can be characterized by a spatial phase theta. Of course, there's also an amplitude of this density wave, and our effective model looks like this, where this term is a local interaction that just wants as much density wave as it can get within a clump, and this is an interaction between clumps where we actually care about this phase. Because this local interaction is quite a bit stronger than the non-local interaction, we can sort of optimize this by parts, set all the chi's to 1, and end up with this effective model. Now, I've written it out here in terms of the x and y components of these spins. And you can see that this lives in a 2D spin space, but the sign here is actually a little bit weird, because if this was sx plus sx plus sy, this would be xy, isotropic xy Hamiltonian. But here, because of the minus sign, it's actually an anisotropic xy Hamiltonian. So thinking a little bit about this model, we know that at high temperature, of course, it hosts a paramagnetic phase. It actually hosts two ferromagnetic phases. So one is when all the Jij elements are positive, then it's ferromagnetic in the spin X component. But if all the Jij elements are negative, it's actually ferromagnetic in the Y component. And then when the Jij is sufficiently disordered, there is also a spin glass phase. And we are working on exactly mapping out the phase diagram here via parallel tempering. Thinking about the order parameters, because the spins are vectors now, the order parameters also get promoted a bit, so the magnetization also becomes a vector, and the overlap we can actually do component-wise and becomes a matrix. So the magnetization vector we can show on a 2D plot. I cannot visualize 2x2 matrices easily, so I'm only going to show you the diagonal elements, the overlap between the X components and the Y components. And so this now is a numerical simulation of an ensemble of J matrices that shows zero magnetization and a smooth distribution of overlaps that has filled in this interior of what is now the relevant domain, this diamond. So that's the equivalent of the Parisi distribution for this system. Okay, so then we can go to the experiment and put 8 BECs inside the cavity. We can image through the cavity with the cavity acting as a microscope and see here 16 spots. That's just to remind you that this cavity always has a mirror image for each atom. So there are 8 BECs here on the right side. The cross here is the cavity center. And so the left half is just a mirror copy. From the positions we see here, we can calculate the J matrix. And this J matrix or graph I can show is fully connected. Now, because this actually is a XX minus YY Hamiltonian, the self terms also matter. That's why there are these loops. And this actually is a ferromagnet. Okay, it doesn't look like any of the ferromagnets I told you about. That's because it has a bit of hidden order. If I flip some of the spins from up to down the basis and make an according change in the J matrix, I can do this local gauge transformation that puts the J matrix into the form that really shows every element here is negative. And so this is a ferromagnet along the spin Y direction. And so the energy landscape of the system is isomorphic to a ferromagnet. The technical term is that this is a one-component Matthes model. So this is just intensity imaging. Now I can switch on the local oscillator and do this holographic imaging where we reconstruct also the phase. And so here I show you the color wheel that represents the field. And zooming in on the 8 relevant BECs and doing a little bit of image processing to average phases, we can reconstruct the spin state that we found. And so we find here this particular configuration up, up, down, down. Of course, you have to remember that because you have to do a local gauge transformation to really show that this is a ferromagnet. If I do that here, I end up with this state, which kind of obviously is a ferromagnet. Now, what comes through less in these slides is actually the specific phase, and there can be slight defects away from the ferromagnetic ground state. We can assess these by calculating the energy of this state that we found. And repeating this experiment many times, making a histogram of the energies and comparing it to the ground state energy. So here I divide it by the magnitude. So the ground state here is at -1. We can find a distribution of energies. And from deriving the local density of states of these ferromagnets, we can fit this with a Maxwell-Boltzmann distribution and find, again, that experimentally we find a temperature that is low compared to the relevant energy scales. And for completeness sake, I can show you the order parameters. So the magnetization of these states is along Y. These are fully magnetized along Y, so either +1 or -1. And the overlap distribution shows these two peaks. So if you generalize again from the Ising ferromagnet to this 2D ferromagnet, this is exactly what you would see. Just the two goalposts with nothing in the interior of the overlap distribution. So to see that, we're going to change the positions. We can program them in, get a different J matrix that is now corresponds to a glassy instance. So again, we can do this imaging. I can clean up the state a little bit, and we see this state with 8 very different colors. This state has no obvious order and roughly 0 magnetization. So it corresponds to one of the local minima that we found that the energy landscape admits. Now, if we repeat this experiment, the same positions and the same ramping schedule, and observe again what comes out, we actually find another state. So these two are not the same. For example, these two colors are very different, whereas here they're close to the same. So this is now an example of this sort of replica symmetry breaking where two copies of the same experiment get stuck in different local minima. Now we can repeat this experiment more than twice, and showing here the outcomes of the experiment. So each spin is shown as we extract the phase of each spin, show different repetitions. This one is not so particularly instructive, but rather from this we can calculate the overlap distribution, and now we see this kind of shape. So again, we find 2 peaks here on the edges of this diamond. Those are corresponding to the goalposts of the distribution. But now we also find peaks in the interior. So these are the non-trivial overlap that this particular disorder instance admits. This is exactly what you expect to find if you do one disorder instance with replica symmetry breaking, where your system gets stuck in the different local minima. Now, what's interesting is that experimentally we can control the rate at which we ramp through this phase transition. So if we ramp slower through this phase transition and create, again, an overlap distribution, now we see that actually we only end up with these two, the peaks on the outside. The peaks in the interior have disappeared because in the experiment we actually no longer got trapped in other local minima. We simply only found the ground state. So this corresponds to a lower effective temperature that is lower than the gap between the ground state and the first excited state. So this is quite interesting. Again, we can try to extract the effective temperature. This is well below the critical temperature for this for the glass transition. But we also have hints and signatures that it's not a thermal distribution again. Now, what's still in progress is repeating this for many disorder instances and seeing the smooth filling out of this diamond that will show us the Parisi-like distribution for this vector spin glass. Of course, there you have to take enough repetitions for enough J matrices. So this is a bit of a time-consuming process. But we at least have seen many of these that have peaks at different locations. This, of course, is more or less uncorrelated due to the local minima of the J matrix occurring at various locations in the configuration space. So that brings me to the end of the talk. Of course, I have to thank all the people that have contributed to this. So this, I think, has been Benjamin's dream for maybe 15 years already of realizing glasses in these optical cavities. So it's been really cool to see that come true. And that's work that I've done, of course, with lab mates. So Brandon has done most of the theory work. And then we have new lab members as well as longtime collaborators and, of course, funding agencies. So thank you for your attention, and I'm happy to answer questions.
Where's the microphone?
Here.
Oh. Questions? Use this to be complete.
So with the network of interactions, how much control do you have in choosing that network, or is it just kind of moving things around and getting what you're given?
So experimentally, we can control the positions of the BCs inside the cavity. There are some constraints, like we cannot make them too close to each other because otherwise the BCs will merge. Because this is also trapped from the side, it means it imposes a rectilinear structure. So you saw on these that they always form like a grid here. Those are pretty much the only constraints. Of course, you cannot make them so far out that they run outside of the cavity, but the J matrix, that form of the interaction, is sufficiently random that you can basically make whatever graph you want. This we've definitely, like, for large positions, these J matrices have the same statistics as completely random matrices. Yeah.
Right behind you.
Yeah, very nice. It's really great to see these multi-mode cavities to come to fruition. What are the prospects of doing this with quantum spins?
Yeah, so these experiments were with classical spins because the density wave degree of freedom is massively populated. The theoretical work was on quantum spins, and we believe this is pretty readily accessible by using Rydberg blockade, for example. If I use Rydberg blockade, where within a clump it's blockaded, so I can only have one Rydberg per clump, then now the Rydberg degree of freedom is a spin-half system. And you can do this in a way that doesn't sacrifice too much of the coupling. In fact, the coupling is the same as the collectively enhanced coupling here, because you still get the collective enhancement from the blockade. So that's the most promising avenue, I think, for really realizing spin-half.
Wouldn't you also need to reduce the dissipation then?
No, actually, the simulations were done for the dissipation rate we have in the experiment. So that turns out to be not a problem. Of course, if the dissipation is way too high, then it kills all the entanglement before you really explore this low energy states. But that seems fine. I mean, all the theory was done with the experimental parameters. So.
Thank you. I think in the interest of time, join me in thanking Ronan for the beautiful. Last talk of the session is given by Stuart. Yep.
No, but it's because it's quadratic. The argument is quadratic. That's sufficient.
I'll take care of it.
Okay, just, yeah.
The last but not the least talk of the session will be given by Stuart Mason from Columbia. Go ahead.
Okay, yeah, thanks very much for the introduction, and thanks to the organisers for the opportunity to speak. For those of you who have long memories back to this morning, my title might sound quite familiar, so I will be talking about something very similar to Susanna was this morning, but luckily with a bit of a different spin and a bit of a different sort of interest. So for those of you who don't remember this morning, I can repeat what I mean by sort of superradiance, and in particular, I guess with the previous talk and a few other talks today, superradiance has kind of many different definitions. And what I want to talk about is many-body superradiance, which is a transient phenomenon where you have an ensemble of excited emitters. So if I start from one emitter, right, I have a two-level system, I put it into its excited state. We all know it decays down to its ground state by emitting a single photon with an exponentially decaying pulse shape. Right? But if I take n emitters, right, then what I get is not necessarily just this, but n times bigger. Right? And this was first pointed out in the 1950s by Dickey, who noted that this simplified picture of thinking everything you can just add up the individual emitters overlooks the fact that all the molecules or emitters are interacting with a common field. Okay. And what that means is, okay, again, we've sort of heard several times over the course of this workshop, if I have an excited emitter, right, and it's just on its own, it decays to its ground state and emits a photon to far field. But if I have another emitter here, I can decay down to the ground state, and that photon can travel over here and excite another atom. Okay. I also now have to have correlated dissipation. If I think I have two excited atoms and a detector over here, and I measure a click and I measure a photon, I don't know which atom it came from. It has to have come from a superposition of both. And so what we find, because of these kind of interactions, is sort of physics that is fundamentally different to what single emitters can do. And as first pointed out by Dickey, he considered kind of the case of emitters at a point where that difference is quite stark, and instead of an exponentially decaying pulse, we have something that is sort of this short, bright pulse that actually initially rises in intensity instead of falling, which happens because the atoms sort of lock in phase. Okay? And because of this idea of emitters at a point, there's a symmetry that simplifies the problem. You can get the same symmetry from having atoms kind of equally coupled to a cavity mode, or as was pointed out yesterday, equally spaced by sort of integer wavelengths coupled to a waveguide mode. And if all of the atoms talk to the field in exactly the same way, then that means that the way they interact in the sort of Hamiltonian master equation that involves this system has to respect that symmetry. Okay, all of the atoms are the same, and so all of my operations onto those atoms have to maintain the fact that they're the same. And if I then think of how does that sort of ensemble of atoms emit photons, well, there's only one superposition of sort of lowering operators. Okay, only one superposition of photon emissions that satisfies that symmetry, and it's a completely equal superposition of every lowering operator. Okay, so if I start from my fully excited state and I emit a photon, the state that I now prepare has exactly one hole, equally likely to be on every single atom. Okay? And in a sort of hand-wavy way, if I look at this, it has correlations in it. It has a phase pattern in it which looks exactly like the phase pattern of this operator. And what that means is the second photon comes out faster. Okay? And that induces more of the same correlations. I now have a state with exactly two holes, sort of spaced on every different pair of atoms. And so the next photon comes out even faster again, imprinting more correlations, and the next photon comes out faster, and so on. And I have this sort of runaway avalanche process, which only runs out when I sort of start to run out of atoms to the emission. Okay? That's what leads to this super radiant burst. What happens if I take this kind of outside a cavity, or outside this limit of all of the atoms talking to the field in exactly the same way? Let's say I think of atoms in free space. Well, atoms in free space, they radiate in all directions. Okay? They don't radiate into a single mode. And if there's finite distances between them, the way they each speak to the mode, whilst they're speaking to the same bath as a whole, they speak to it in slightly different ways based on how they're arranged. Okay, and so generically, if I have a system of n atoms, my system bath coupling, I can diagonalize this into n different decay channels. Okay, I can think of this as my atoms have n different types of photons that they're able to emit. Okay, and each one of these channels has some associated decay operator, which is some superposition of lowering operators of some or all of the atoms. And each one of these operators comes with an associated rate of action. Okay, this gamma nu. And these things are found simply by diagonalizing an n by n matrix. Okay, so I can find these things for large systems of atoms. But then if I want to apply this to actually solve the problem of Dickey superradiance in these finite systems, I run into a problem. And it's a problem that's very familiar to people in sort of many-body physics, which is my Hilbert space starts to scale exponentially. Okay? So I think of that case of kind of atoms in a cavity, atoms at a point. My permutational symmetry limits me to a number of states that scales with the number of atoms linearly. Okay? So this is easy to do for huge numbers of atoms. Similarly, if my atoms don't talk at all, they're so far apart that they can be treated as independent, then again, it's easy to do large numbers of atoms because I don't need to worry about correlations between them. But in this case, where I have atoms sort of closely spaced enough that they talk, but not at the same point, then I don't have my permutational symmetry to restrict the states that I can enter, and I do need to worry about correlation. So I need to worry about something which now grows exponentially in the number of atoms. Okay. Okay. And so this has led to, you can find papers in the literature going back to kind of the late 60s, early 70s, talking about, well, what happens in these systems, these extended systems? Okay, can they emit super radiant bursts or not? And there's arguments back and forth, but I think it's generally accepted that interactions between the atoms, these coherent interactions between atoms, will lead to a dephasing mechanism, okay, which will mute or kill super radiance. Okay, but coming up with some qualitative picture of whether or not this happens is entirely non-trivial, except for the fact we can do experiments. Okay? And so again, going back to the first paper of 1973, Dicke superradiance definitely occurs in these kind of extended systems because it's been observed. Okay? And now it's been observed, I think, in kind of this myriad of different platforms, ranging from thermal molecules through to sort of artificial systems. But modeling any of these quantitatively as a theorist is really hard. Okay? And the reason for this is that these systems are not dominated just by these kind of collective decay mechanisms that I mentioned a few slides ago, but also by single atom effects. Okay? If I think of sort of these kind of thermal gases, then I have things like Doppler shifts, okay, causing an inhomogeneous broadening of all of my emitters. If I think of things like quantum dots, there's an intrinsic inhomogeneity by the fact you can't fabricate every single quantum dot to be exactly the same. But most insidiously of all, if you want to do this in sort of a dense medium, those coherent interactions, those sort of flip-flop exchange interactions that I mentioned in a dense medium are strong, and they cause frequency shifts. Okay? But each atom sees a different set of atoms around it. Okay? It sees atoms at different distances from it. And what that means is, again, we have some sort of insidious inhomogeneous broadening, which just comes from the fact that they're interacting at all. And so what I want is something which has the complexity of this kind of multi-channel decay, where I can emit different types of photons and then look at an interplay of different decay channels. But I want that to be the dominant thing. I want the collective behavior to dominate the dynamics and not have to worry about the sort of inhomogeneity that comes from most of these platforms. And this is where the second half of the title of my talk comes in, which is thinking about doing these kind of experiments, but with atomic arrays. Okay. So I'm sure I don't have to explain to anyone here what these kind of platforms are. It's arrays of single atoms held in optical tweezers, which can be now arranged at sort of nearly arbitrary locations with essentially perfect filling fraction. Okay, and we can arrange atoms however we want, and then do sort of quantum optics experiments with them. Now, what's useful about this and why we think this should lead to something where the collective behavior is more important than these kind of individual things is, I said that the most insidious form of inhomogeneity comes from the fact atoms see different sets of neighbors. But if I look in the bulk of these kind of systems, they all see the same neighbors. So the frequency shifts they get from their coherent dipole-dipole interactions should be reasonably homogeneous, which should allow the dynamics to now be dominated by those collective dissipative interactions that I talked about at the beginning. And these types of platforms are being built kind of all around the world now, and it would be remiss of me not to mention that includes Colombia, where Sebastian Will's group is using these sort of passive metasurface devices made by Nanfang Yu's group to trap arrays of strontium atoms. And this slide now has an update coming very soon because we now have sort of signatures. There are atoms in tweezers, and so hopefully in the reasonably near future we will be able to do kind of the sorts of experiments I'm motivating in-house, which will be very exciting. Okay, so my argument here is that the superradiant burst should be more robust in these kind of ordered systems because we've gotten rid of some of the inhomogeneity of having kind of disordered clouds. So let's have a look at what the dynamics are. Right, this is a chain of 8 initially excited atoms. I allow them to decay, and I look at the light that's radiated sort of everywhere and integrate kind of over 4 pi. And you can see in the case of sort of Dicke's case of everything at a point, we see this reasonably large superradiant burst. I increase the distance to something about 1/10 of the wavelength, and I have something which I'm still going to call a superradiant burst, but it's still shorter and sort of brighter than you'd expect from single atoms, but it's not as bright or as short as you expect from Dicke's case. Okay. But then as I increase the distance again, I now see something which is just monotonically decaying. Okay? So from t equals 0, the intensity that's emitted just keeps getting smaller. And so what's happening here, right? I argue that this shouldn't happen because of these kind of coherent dipole-dipole interactions causing inhomogeneity. But instead, I have dephasing that comes from a competition between all of those kind of different channels that I talked about at the beginning. Okay. So Dicke superradiance, remember, is this avalanche process where I have a fluctuation that imprints some phase pattern which enhances more photons, and so I have the runaway avalanche process, right? And if I can emit multiple different types of photons, each of them does the same thing. Okay? Every type of photon I can emit imprints correlations that make more photons more likely to come out. The critical thing is that they enhance the likelihood of photons of the same type, right? They enhance themselves, they don't enhance one another. Okay. So if I go back to this picture, I look at the sort of Dicke's case, I only have one jump operator that can act at that symmetric superposition, and so I have an avalanche process, okay? And now I go to kind of 0.1, so a tenth of the resonant wavelength. Here, out of my sort of n channels, only 2 or 3 of them are likely to have photons emitted into them. Okay, so each of those then does its avalanche process, but I have a finite number of atoms. I have a finite quantity of snow, okay? And so none of the avalanches can get that big, right? And that's why we see this muted superradiant burst. Once I get to 9/10 of a wavelength, there all of my operators are very likely to act. And essentially now I have so much competition, there's just not enough snow to go round, and none of those avalanche processes can get started. Okay. So I can explain what's going on now in these systems from this picture of just the kind of the collective dissipation. And so the idea is, well, what else can we do with this? Right? What can we learn from thinking in this kind of collective pictures where we can argue that this is reasonably well explained solely from this sort of collective dissipative picture? And we can start asking questions like, I showed at the beginning, people can put arrays now into all different sorts of patterns. How does that impact the light that comes out? Okay. And again, I can do some exact calculations here for 16 atoms. And you can see that the geometry, so how I arrange my atoms, is definitely very important. Right? My 4x4 square array has a much larger superradiant burst than the 16 atom chain or the 16 atom ring. Okay? So geometry certainly plays a role. But the issue here is I motivated, the whole reason to do this with arrays is because the atoms in the bulk all should behave the same, and I can treat this as a collective system. And I have a 4x4 that doesn't have bulk, right? It's almost entirely edge. So if I want to move to something where I have this sort of truly dissipative system, I need more atoms. But I can't have more atoms because of the exponentially large Hilbert space. So what we need to do is be smarter, right? And what we did was, well, we noticed that the burst doesn't just get smaller as I increase the separation between my atoms. It also gets earlier and earlier in time, such that when it disappears, and here I'm using a definition of superradiant burst just to mean that the slope at t equals 0 is positive. Okay, when it disappears, when that's no longer true, it happens at t equals 0, which means that that kind of avalanche process driving the superradiant burst either has to happen immediately or it never happens. Okay? The emission of the first photon has to enhance the rate of the second photon. And to quantum optics people, that's just a second order correlation function. And for the fully excited initial state, I can calculate that exactly and find my condition for this superradiant burst, for this initial positive slope, comes out to just be the variance of the set of collective decay rates. Okay? So you remember from several slides ago that these are just the eigenvalues of an n by n matrix. Okay? So I can construct this generically, I can construct this for in polynomial time in the number of atoms, but actually because of the ordered array, you can use some tricks and you can evaluate this thing in linear time in the number of atoms. Okay? And so I've gone from kind of exponential scaling to linear scaling at the cost of now I essentially just get a binary piece of information. I get superradiant burst or monotonic decay. Okay, but I can get that for really large systems. What we can do, okay, we can compare this now to exact simulations for small numbers of atoms and check that this is correct. We can see when my condition says there shouldn't be a superradiant burst, indeed the time of peak emission is at t equals 0. Okay, the brightest the atoms ever emit is initially, and you just monotonically decay from there. But the moment my condition says that there should be a superradiant burst, we now see a time of peak emission that it is at some finite time. So the intensity kind of increases and then falls off. Right? And what we can do is we can set the condition to 1. Right? We can find kind of the crossover point where you go from monotonic decay to the superradiant burst. And we can do that for kind of different geometries to compare how this physics manifests in different systems. And so this, not only is it a sort of a very neat expression that's easy to calculate, I like to think it also gives some intuition about why this phenomenon happens at all, right? Which is, okay, I need the variance of these set of decay rates to be large, right? But I have a fixed mean, and they're decay rates, so they can never be 0. Okay, so how do I make a set have a large variance when I have a fixed mean and I can't be negative? I could either set a bunch of them to 0, which then lets the rest of them be large enough to drive the variance up, okay, which would be achieved through sort of destructive interference, that there are channels that the atoms can't speak to because they destructively interfere into that channel. Or I can just make some of the decay rates really large, okay, which comes from kind of a constructive interference that the atoms all sort of really want to speak to certain modes. Okay? And so the question is, which of these happens in ordered arrays? So we can start with 1D arrays, and we can calculate this condition, this crossover point, kind of critical distance where we go between monotonic decay and a superradiant burst. And you can see it depends on the polarization of the atoms, but ultimately it's about something of 1/4 to 0.3 of the resonance wavelength. And it seems like it saturates as I increase the number of atoms. But I can go one better than that because I have sort of a periodic system. And so if I think of an infinite periodic system, I can always do a block wave decomposition, which means now instead of thinking of my collective decay channels kind of in terms of these like nus, I can instead think of them as having an associated wave vector. I can calculate exactly what the decay rate is as a function of that wave vector, which is what this is for 1D. And then I can recast my variance expression instead as an integral. Okay, and we can solve this and find the distances at which this thing is 1. And when we do that, we find that not only should it should saturate to exactly the values that our numerics did, which tells us these 1D arrays of atoms, actually just having kind of a few hundred behaves pretty much the same as having sort of an infinite-sized array. But from my finite number of atom simulations, we had remember that 2D did much better than 1D. It emitted this much larger superradiant burst. So do I see the same behavior now in this? And the answer is yes, in multiple ways. Okay, so the distances that the atoms need to be separated to still be able to see a superradiant burst can now be much, much larger. And as we increase the atom number, they diverge. Okay, and we can again do the same integral now with the 2D decay rates, and we can find these kind of plateau sections diverge as the square root of the logarithm of the number of atoms. Okay, so it diverges slowly. But you do get these kind of occasional help from these like geometric resonances, whereas you increase the distance between atoms, at some point you have kind of an extra umklapp process is allowed, which sort of drastically changes the rates at certain points. And so globally you do scale a bit faster than that square root of the logarithm. Now 2D it sort of has much larger distances than 1D, so you'd be correct to assume that 3D does even better and now diverges even faster. So here our integral tells us that it should diverge as a power law, but we end up hitting these kind of the geometric resonances that I talked about. You end up hitting them so frequently that actually finding a plateau long enough to fit is impossible. So instead we fitted the whole thing to a power law, and that also seemed to work reasonably well. But what you can see is here this diverges much, much faster. And now the distances that atoms can be separated in these types of arrays to see the physics is much, much larger. And if you think back to Dickey's original paper, he says that the superradiant burst should happen if your atoms are all confined in a volume that's much, much smaller than the resonant wavelength in all dimensions. But what we've now shown is that the same physics can actually be manifested somewhere where each atom's nearest neighbor is actually several wavelengths away, which is kind of fun. But why are the dimensions all so different? Right? That was the question I motivated at the beginning, was, well, how does this superradiant process happen? And the reason things are different is because in different dimensions, different physics is actually driving the superradiant burst. So in 1D, it happens entirely because of this destructive interference, because many of the decay rates go to 0. Okay? Whereas in 2D and 3D, it's happening at distances where there aren't dark rates anymore. Okay? And so it has to be coming from constructive interference. Okay? And this is then why the behavior is so different. If you think one of them comes from destructive interference in 1D, once I have enough atoms that I'm approaching things being 0, I add more atoms, I just get infinitesimally closer to 0, and that really doesn't change anything, so I just saturate a bound. Whereas in 2D and 3D, I have these divergent rates. The more atoms I add, the brighter and brighter those particular modes are, and the further separated my atoms can be. Okay, but I sort of started this talk by talking about, these atomic arrays are an experimentally viable platform that's being created around the world, and a few slides later I've ended up talking about infinite arrays of two-level systems with light being kind of collected in 4 pi. And so the next goal is to bring this back to something that people could actually measure and could look at in realistic experimental systems. And so what we thought about was doing this with alkaline earth atom arrays, or I should say alkaline earth-like atom arrays, because the two species we considered, one is strontium. So this is a picture of a strontium array from Adam Kaufman's lab. This is actually a picture of an ytterbium array from Jeff Thompson's lab. And so ytterbium isn't technically an alkaline earth, but it has the same bivalent electron structure, which gives it the set of levels that we need to be able to sort of look at this physics. And that structure is having these kind of long wavelength transitions to metastable states. So these 3p2 and 3p0 states are very long-lived, and these transitions to them are at infrared. Okay, so what you can do with these atoms is you can trap them at sort of optical wavelengths, so you can get them sort of close together. And if you think back to all of my previous slides, all of the distances I was talking about were always in units of the wavelength of the transition. So if I use a long transition, the atoms look much closer to each other, and we can sort of trick the system. Okay, so in strontium, these transitions range from sort of 2 to 3 microns, and in ytterbium they range from about 1.5 to 2, which is particularly exciting because some of them are actually at telecom wavelengths, and so doing experiments with these, you already have kind of components and detectors and sources and all these things ready to go. Okay, so there is one, I guess, elephant in the room here, which is this is definitely no longer a two-level system, right? What we can show is that we can simplify down all of this level structure by looking at kind of toy models of these multi-levels, of sort of multi-level atoms in cavities, going back to Dickey's case, so kind of the permutationally symmetric basis, and do kind of simulations. And you can see here, okay, I have an atom in an excited state, and it can decay to 2 different places. You can look at the light that comes out on each of these 2 transitions, and you can see that, in fact, in this case, not only does the superradiant burst survive, but it can actually be seen on both of the transitions. And then if you look at how these things behave, kind of as you scale the number of atoms, you see that if you have kind of a dominant transition, in this cavity case, your dominant transition now has a peak that scales as n squared. So your dominant transition retains Dickey's thing, and it goes back to this being an avalanche process. Because my first photon is more likely to be emitted on the brighter transition, that means the avalanche on that transition starts first and steals light from the other one, which means then if I look at how much light was emitted on each transition, as I increase the number of atoms, more and more light gets emitted onto my dominant transition. Okay. The other thing we have in these systems is these kind of things, where you have an excited state that can decay to an intermediate state that then itself decays down to a ground state. And what we find here is as long as this decay isn't much, much, much faster than this one, you actually end up with this kind of sequential superradiant burst type thing, where a burst comes on the first transition, and then a second burst comes on the second transition afterwards. And again, we can explain this as avalanche physics. The first process happens so fast once it gets going, but by the time this one gets started, the first one has already finished. And what this particularly unpleasant looking graph is here is, again, the scaling of these with different rates. And all of the points just sit on top of each other because essentially the properties of this first burst don't really depend on whether or not there is this secondary decay from the intermediate state. And so that means if I want to start in, let's say, the 3D1 state of my alkaline earths, I can ignore these two, because these two decays are so weak that they'll essentially just be closed off by this kind of collective behavior. And I can also ignore this one, okay, because this is one of these cascaded things where it's true there would be a secondary superradiant burst emitted here, but it won't actually alter the properties of the first burst all that much. And so I can turn my complicated level structure into a 4-level atom. Okay, so I want to start in, let's say, the 3D10 state. Okay, my dominant transition is this pi polarized one here, and I have these two other kind of parasitic decays to different levels. And I can now put my my array of ytterbium atoms and see what light comes out. Okay, so now I'm thinking of light being measured by a detector in a particular position. Here it's in the plane of the array. It's only measuring light emitted on that bright sort of dominant transition. And I can look and you can see that, yes, a superradiant burst should be observable at distances which are maybe sort of slightly optimistic for tweezer array experiments, but are certainly achievable in optical lattices. And you can see as you increase the distance, as you would expect, my superradiant burst sort of goes away, and now I just have exponential decay. And then I increase the distance again, and it comes back. Okay. So this highlights kind of the highly non-trivial nature of decay in these kind of ordered and collective systems, right? Emergent behavior coming out of the complexity that you might not necessarily expect. But luckily, we can predict it pretty easily by using kind of a modified form of the condition that I sort of showed on the variance, that now this takes into account the fact I only want to measure light on a particular transition that's sent in a particular direction. But I can map this out, and making one of these takes 2 or 3 minutes, and I can find, I want to do this fun reveal for a talk. I can find exactly where I should run 3 simulations to get the lines from the previous plot. Okay, I don't need to scan over huge realms of parameter space. Whilst that's good for me, it's not necessarily that useful, but what we can do is the same thing for experimentalists. Okay, we don't need to, calculate the dynamics at every single position to be able to do things. They don't need to run their experiment in every single parameter regime to do things. We can point them in the direction of the physics that they're interested in solely by making predictions based on this kind of collective behavior. And maybe the experiment that you'd be interested in doing would be just to measure like the largest superradiant burst you can from one of these ordered structures. And so there you want to look at the longest wavelength you have, which is this 3D3 to 3P2. Again, you have something where you have kind of 3 decay paths. You also have this nice 2-level transition here. And so here, I'm now thinking about strontium, whether that transition is longer, in a 12 by 12 array at sort of a distance that's relevant for optical lattice experiments. And you can see now that you get this sort of large superradiant burst. And by looking at different atom numbers, we can show a scaling that, whilst it's not the n squared predicted by Dickey for atoms at a point, is much faster than linear in the number of atoms. Okay, so you have some sort of intermediate scaling of the number of atoms. Or perhaps you want to go back to those kind of toy models in a cavity and look at these kind of ideas of closing off weaker transitions, right? So they take a single atom in free space. The relative decay rates that can decay to different states is given to you by atomic physics, right? You can't fight that. It's given to you by Clebsch-Gordon coefficients and dipole matrix elements. But you can fight it by using collective effects. So again, just as in the toy model, the more atoms I add, the more light will get scattered onto the brighter of the brightest of the transitions. And you can look at this as a function of playing around the interatomic distance, and again comparing to kind of our superradiance condition. And you see there are bumps in the collective behavior you'll measure in this sort of light share that match the bumps in the superradiance condition. So again, we can point out where you expect this thing to matter more or less, depending on whether you want this effect or it's going to cause you problems. Okay, so that's, I guess, the story of superradiance and arrays. I'd like to take a few minutes just to highlight some other things that we have going on. Also kind of related to collective scattering in different systems. So this, I guess, slightly nervous to talk about given how many people here work on dipolar condensates, but we think of this just from a quantum optics perspective. I don't need to know what's going on in the condensate. We can revisit experiments if you take sort of a cigar-shaped condensate, you shine in light from the side, and it wants to shine light out of the ends. Okay? And in doing so, it creates these matter waves that you can measure. Okay? These are experiments first done down the road at MIT in Wolfgang Kettley's group. But what you can do with a dipolar condensate is you can break the symmetry. Okay? You can make, by kind of moving the angle of your magnetic field, you can make it more or less likely to produce excitations in kind of one direction. Okay? I can break the symmetry of wanting to emit left or right, and we can see you have these kind of big these sort of shifts in the value of how many atoms are in each of these matter waves. And what's particularly interesting here is you see these really large fluctuations in how many atoms they see in each of the things because of these collective effects. Okay, we expect this shearing of the average, but also extra shot-to-shot fluctuations on top of this. And so, yeah, that's sort of experiments done in the group of Gieb and Zhou in Hong Kong. And also looking at, on a much smaller scale, collective scattering of a tweezer array into a cavity. So these are sort of some preliminary results from Dan Samper-Kern's group, where if we sort of look at the red data here, we have a tweezer array. You put it inside a cavity and you shine light from the side and you measure how much light comes out. And this curve, you've placed the atoms at points where you expect them to constructively interfere into the cavity. And you see this close to n-squared scaling in how much light you populate your cavity with. Whereas these data points down the bottom or in this inset are done where you're now putting atoms in sort of alternating plus and minus sites of how they couple to the cavity. So in theory, they should then destructively interfere. Instead, you see this kind of zigzag pattern where the odd numbers of atoms scatter much more, because there you can't perfectly add up them plus and minuses. We also have some things on these kind of things from like a waveguide QED perspective. So instead of atoms talking through free space, where you generically have kind of n modes, we now just have two modes. Okay, we have left and right. And you can show that Dicke superradiance still occurs. We can look at the same kind of things in terms of kind of looking at fluctuations in how much light is sent in either direction. We have sort of a project of, what I've talked about today was kind of thinking, I get this binary piece of information just by looking at dissipation, but what else can we learn? Okay, how much can we reconstruct about the light that's emitted just from looking at these kind of collective pictures? And then on a slightly different note, working with Oriol and Susanna, we've been looking at being able to kind of use collective dark states that show up in these waveguide QED systems by stabilizing those dark states and then carefully kind of destabilizing them in a controlled way. You can arbitrarily shape sort of photon pulses, so single photons, or this is 2 photon pulses, or even more complicated things, and you can ask Oriol for details on that. And so yeah, that's everything. And so just to kind of conclude, I want to point out that atomic arrays provide this new kind of exciting platform to do many-body physics in a quantum optics setting, where we have this kind of programmable, precise, reproducible way of arranging atoms and getting them to interact with light to do things that we can't otherwise do. And then everything I've talked about today is sort of realistic and could be done in state-of-the-art systems that people already have. So yeah, thanks very much, and happy to take questions.
Multitasking is good or not? Yes.
Very nice. Okay, so.
Let me see. Just in case.
Thank you. So I have one question is, what is the role of the elastic interaction? So I think my understanding is the system is order and then elastic interaction doesn't matter, but you start to have defects, then they play a role. So when you are going to the lattice that is not completely ordered, what you think are doing the modifications?
Yes, so certainly everything I showed today was thinking about perfect lattices, and that's not actually experimentally feasible. But with one of the things that's great about working with superradiance, which I think you can see by kind of looking at the experiments from the 70s, is it's really robust, right? It still shows up when you have all sorts of noise. And actually with an imperfect array, all of these results, your burst might be slightly smaller, but you still see most of the same physics as long as your filling fraction is reasonably high. So if you have a few atoms missing, everything basically behaves pretty much the same. If I have 80% of the atoms missing, then obviously not.
And becomes dominant for short distance, yes, because is 1 over r cubed.
Yeah, so you can also put in sort of positional disorder. So yeah, here we've been thinking solely about pinned atoms in perfect positions, but yeah, if you allow them to slosh in the trap.
No, it's just one scales like 1 over r cubed when they become closer, so it's not going to be very important when the distance is smaller.
Yeah. Yes, yeah, so those kind of effects, yeah, they will start to matter if you want to do things at very small distances. But yeah, so small positional inaccuracies at these kind of scales don't have a huge impact. That's correct.
This is a 10-second question and a 20-second answer.
Thanks. So you mainly talked about the platform to be atom arrays. And I think one of the real advantage of it is that you can arbitrarily arrange 2D patterns. You did show that in 1D, being in a circle versus being in a line doesn't matter too much. But in 2D, do you have any plans about non-square systems? And if truly square system is what you're most interested in, then maybe optical lattice can achieve smaller spacing.
Okay. Yeah, that's a good question. I'll go for a 20-second answer. So we looked at different lattice shapes. Okay, so we looked at triangular lattices, hexagonal lattices, all the things that people commonly make, and that doesn't really seem to make that much difference. Okay, the key thing that changes is when I can change the dimensionality. That makes by far the biggest impact. So yeah, you can definitely optimize the geometry. Square actually isn't perfect. The best is a triangular lattice because you basically have like a higher packing fraction. But the impact of doing that is very small. So being able to keep it in something where optical lattices is also a platform that we look for and keep it more general, I prefer as the talk. But yeah, we did look at that. It's in this paper.
Thank you. With that, join me in thanking the steward and So there is a poster session going on for a while. We've all been fed properly, so we can have a late dinner. It's over there. Thank you.
Do you know how to turn this off?
What?
Oh.
No, I will probably follow some with a bit of instruction that I might do.
It's not quantitative.
Yeah, the competition between kind of super radiance and so now I have need your hot announcement.
Especially it seems like to really understand that continuous time crystal you need all
inherently comes out.
We are calculating 5 times 5. So with 25 nodes to kind of get recurrent variance to what we see.
Yeah.
Yes, actually,
so yeah, what you calculate, you essentially just want
all higher line nodes.
I want my first waveform to announce my second, that means this one is very so I can express this as overall amount.
But it's still like not 1 or 2, but it's like
this and then normalize
times
them.
5, something like that.
And then yeah, when you calculate this out,
you take
it
another
gives you
layer of
this is
nodes,
equal to 1 plus
results don't change anything.
I think it's the variance minus 1 over m or something like that. And then you can then say for this to be larger than 1, well,
Like many
that's,
things actually,
you just need this to be larger.
it's only the rooted
So you can just express it. The physics essentially is just, you can also calculate exactly the same expression by just calculating the slope at
the red, yeah, we have
so Francis Frobisher has a paper where he got like he saw our paper and then he'd been doing these calculations of looking at the slope, and he realized our paper gave him exactly the same result.
So maybe
and then he worked out that there's actually this thing is the physics is.
But you say you can calculate this?
No, so this thing, so we calculated this just as t equals 0. And then because the initial state is this, and then the key breakthrough was in realizing these things are eigenstates. So these are all. That means if you evaluate this thing, it's 1 plus delta t minus.
So in the experiment they do have like one system because they have
I guess this is geometry.
and there is a drive.
So the question is,
No, I mean, yeah, all we get out is this binary thing. And yeah, you're not limited to just this type of state. Anything that's not correlated. Right? I can calculate these things. We focus on this because it has the historical significance. Yeah, that's actually myself, the student who's been looking at how much further can we take this. It became, started off as, we can get a higher order of this and see what happens. And yeah, it becomes, learned a lot more about combinatorics. I think we should have something to learn. But yeah, it's,
this clarified my question.
okay, great.
Thank you.
We also started
So now, because again, what happens when you are going then you have a different potential, but that's modifies and becomes exactly as yes, let's have exactly. That's the most important part. So now what happens when I have a system, when I have
antibody effect,
and I have
yeah,
the order of them. So then
you have the same kind of
what happens is that
interplay.
if one was eliminated,
The decay becomes high, non-trivial.
then you are going to have two-body interactions.
No, why? This is the possible place.
You're going to have three bonds. And you have higher order interactions. So
even in like the case of the atom thing,
what about this idea
Yeah. So yeah, this thing emits the lyrics, this thing.
Exactly.
This thing actually also emits
Exactly. It's the
yeah,
same.
you have something where it's every state in the case behaves at the same level. And so to see the first, you need
And you get analytic expressions
so
for
you need at
this
least a
kind
third
of
action
efficiency.
so you can make that.
That depends on like kind of if you're in a simple like two-level model, I think you should.
And as for the proposal you had
I mean, like, yeah, because you have just
do you remember the
average of 53 and P2
Yes, imagine that this is not the case. Exactly. So, because I mean, we try, but the analytic expression get very messy.
Yeah, so if you just go from like this one to like just
yes, exactly.
They're not super.
Yes, but it is complicated because you are going outside the lithium manifold. Yes, so for example, if you have, so for example, you can have,
you still have like
you have the symmetrize, then you can try to do yeah, I mean, yes, exactly. So you get an analytic expression for that. Okay.
I don't know much about this. Yeah, so there's two ways you can think of preparing these things. One is, now it's more like the but they do basically like repeat the result Raleigh pulse.
It breaks down.
So it kind of happens in like a way.
Yes. Yes, exactly.
So if you could do something like that in free space.
Yes, yes.
Speaking with they can do things like that in free space. Then you flip all of the atoms on the scale, but so far
no, but we have tried, but the analytics looks very messy because it depends on the rapid drive and the decisions between all these different inputs. Well, so what we have done is that, for example, for three particles, we transform the ground state of the system, yes, and three particles. And because the regular procedure is that you complete the ground state of the system and subtract the energy of the lower states. Yes. So, for example, for three states, no, we have to fully diagonalize everything because you have to consider the items. Now you have the atoms and you have all to the 2 to the 3 states. And the yes, to the 3 states, and then you try to compute the state. But it scales very bad. And I mean, we were trying to do brute force, like not perturbation, but trying to compute the energy spectrum of these. And then subtract the body energies.
But I think it's just a matter of laser machines, and you could think about doing the lasers to do this experiment.
And then like do this like just by
convince me.
Yes,
As long as we have the lasers, it should be possible.
That's what, but you don't do that.
I mean, like kind of, I think from kind of the theory of this principle, that's not specific, but I think before, myself as an MPI, I want this to be given this talk, and then people are like, but then this is exactly for that reason, so I think maybe building the Chavian arrays, well, I think expansion plus from
Okay, and do you have
any to do this, and it's like, you help us with the atomic physics to make sure
I think like kind of, I don't know.
There should be a roadmap like here is like this works.
Exactly.
It's not a problem to find out the higher orders, but if you need like what I saw like these arrays of
lots of challenges with
really need like
almost every experiment.
Yes, that's the problem.
So the transition looks nice. One line over. So the time scale of your burst is also reasonable.
Yeah. So if you had, the closer you get, the shorter the burst.
Because when I left, it was still there. Yeah, exactly. But now there's only one up. Yeah,
I think you just didn't meet one.
It is mine.
Yes, exactly.
Okay,
This
then.
is right.
So you
Yes.
have yours. So I kind of now I can add them, and then maybe I see some. Okay, good. Then I just add them. Effective two-body interaction. Oh, that's effective three-body interaction.
Yes.
Great, thanks. Then
I didn't catch your name, by the way.
Nishad.
Nishad.
Ronan is like collaborator from my old cabbie days. So collaborator, like discussion partner.
Discussion partner. Yeah, we never seriously collaborated.
Exactly. Yeah.
So are you?
I am defending in 3 weeks, so I'm maybe soon to be a postdoc. Who knows?
Doesn't work. Well,
What's next?
Maybe soon to be a postdoc, or
is
yeah,
it
maybe
they're
industry.
kind of
What?
affordable?
Oh, rich.
Or rich, yeah. We're rich, that's
exactly.
What about you? You're a PhD student?
I'm a grad student.
And how far along are you?
I'm finishing my 4th year now.
Okay.
Yeah, so probably 2 more years.
Adiabatic ramp.
And you mostly theory?
Yeah,
Exactly.
Went to the lab.
So maybe.
They were, after that they were like, never again.
Leave us alone.
The first time I gave this talk, after they actually trapped atoms, I had to like email the student, be like, I've never been to the lab. I think I need to come to the lab. If anyone asks me questions about what
like
I actually
literally
did,
anything.
no. now I know, so it's fine.
Yeah, it's good. I think at some point, like I went to the experimentals and I was like, okay, I'm gonna sit down and you're gonna like just grill me for an hour on how your experiment works, and let's see what I can and can't. So yeah, I was like loading that. I was really I didn't have no idea until that day.
Until they go where they start
one
very
atom
far
per tweezer.
and they go to the
Because
point
funny
where they want
probabilistic
to
thing,
do
you
the
load a
dynamic.
bunch and then
Then
you
they stare there.
Just wait.
Yeah, that's actually, my slides should be updated again, because that's they had atom, when it says atoms trapped in January, that was just atoms, that's what he said. But now they've done the collisions and they have one atom.
One atom per tweezer. One atom and half the tweezers.
Yes, they don't have the rearrangement yet. That's one of the meta surface thing they're using to trap. Doesn't let you rearrange it. It's passive. Like it's literally a device. Like it's a flake of titanium oxide.
Yes.
Okay.
I think.
Interesting.
Yes.
So then, they need to buy an AOD to actually to rearrange it when they're ready to do that.
Okay. Cool. No, but yeah. That's fun stuff also.
It would be great. I mean, it would be fantastic. I mean, we are trying to do another project that is good for numerics.
Yeah, I also think so. I mean, I think we should not kind of completely kind of
some way,
leave
but
things out
I mean,
because they are too naturally there. Sort of.
Plus, every experimentalist has cried a little bit when we show them all sequences.
Yes.
But the thing you showed was some smooth evolution of a parameter. Yeah, the phase or something.
The amplitude.
It's like there's 2 phases. Exactly. We do hyperfrying and reverse driving.
Yes. Exactly. So, it's not super bad.
Yeah.
But it's still smooth.
At least you didn't come up with anything discontinuous.
Oh, we have those as well. I can show you many of those, like much more than these.
Therefore, are they more efficient too?
To some extent, yes. But I mean, both. I think both of them are perfect.
The problem with these optimizer things is a lot of it is like, how hard is it?
Yeah. It's pretty random in a sense. What do you find here?
They often find like really wiggly things, which actually are just a very small improvement over something that wouldn't make somebody grow.
Exactly, but that's exactly
because of the way you find it. It's sort of obvious how to find the smoother solution.
Yeah, no, but that's what we have. We can kind of introduce a penalty to the loss function.
Okay.
Like if the change between neighboring times is like too big, it's increasing the loss basically, and that's helping.
Hello.
Yeah.
Yes. Like 1 second is like I have to find my phone because I don't see it. Very bad.
Would you like one of us to call it for you?
Okay, thank you. It was here with me last
Sure. What's the brown paper?
Okay, thank you.
Actually, this is something you might be interested in.
I guess your watch is telling you it is close by, right?
The red data.
No.
Basically, they're not selecting the magnetic signal. They're just putting the atoms into the
Oh no, is that the watch ringing?
No, but
I think it's here. Isn't this here?
Oh,
Or,
okay.
yeah, okay.
Yes,
No,
yes.
good.
It was the same that is out of frame.
Ah, okay.
Okay,
Oh,
thank you.
interesting.
Okay,
Was it
great.
a Faraday cage?
Yes.
Exactly
Yeah.
equally.
Yeah, we want to do like discuss of like your idea with the dressing.
Ah, I see,
for the-
because
for the
we have a
customers,
paper, but we can see, we have seen that it's very efficient.
Yeah.
Okay.
So,
Theoretically,
it's very
super broad
efficient,
thing,
so,
yeah, we were just to see the right visit. But the brand data is, they're much
so,
closer to presence.
imagine what
And then
we,
the atoms
we're doing
preferentially
is the following.
scaling
So,
different state preference in phase.
you have
Essentially,
Hamiltonian where you
the
have
brand data,
the
they see
icing
it just
interactions,
like
I,
plus
sigma
minus.
j,
And in the other case, they also
and
scatter
then you
into
have the
plus
Bij,
minus.
and this Bij
They scatter
depends on
instead of all of
is
they,
this,
okay, in the first
is
brand
this,
data, they
of
just
course,
scatter
sorry,
into
my
X.
drawing is
And then the
bad,
brand data,
something like
they
this.
scatter like 80%
So,
to X and 20%
this
to
is
Y.
just icing, this doesn't,
that
see, this
messes
is not
around.
collective,
So-
I mean,
Yes.
it's bad, because any perturbation brings you away, but if
Yeah.
you add a
Yeah, that's
strong
that
drag,
we worked out the red
yes,
data, and it's
so
like
in
basically
this
just means
case,
like integrate out
this
the atoms.
Hamiltonian,
Because whichever MS state they're in,
you
they
can
scatter
see
exactly
that,
the same way.
but let me change the index, I mean, just rotation, this is XX, this is
And then in the
CC,
other
just because it's
They
easier
want
to
me to
drag.
it's like
Okay.
five little atoms.
So you can see that this Hamiltonian is
behave
sigma
collectively,
plus,
so it
plus sigma
scales
minus, yes?
with
Yeah.
n, and it's a
So
bit tricky.
with omega is very large, the
So
fast rotating
it's
strength
still-
disappears,
it's still-
and
I
then
think
you
that's
get a
honestly
Hamiltonian that is sigma plus,
So yeah,
sigma
we can
minus,
definitely qualitatively do
plus
things,
sigma minus,
but yeah, at the
sigma
moment
plus.
it's like
Yeah.
for the number of
And,
atoms they have, it should.
and this
be something
Hamiltonian
bad.
is equal to
I think if the
sigma dot
theory
sigma
might be in more of a
minus
state of,
sigma ci, sigma ci.
working.
And,
The
and it
experimental data
happens
that British done,
that
Gigi actually
in
sent me
this case,
some data this week. They now basically
this
this like
Hamiltonian,
polarization things, how much X
because
you get
this
per
you
turn.
have the soft core,
You get
it's
like
so
my theory
robust,
says
I
the
mean,
more atoms they have,
it acts
the
as,
purer the
this Hamiltonian
polarization
acts
should get.
as
Because you're
as
scattering
S
into
squared
X behaves kind of
minus
collectively.
SC squared
And into
within the
Y, it's still
blockade,
actually
very
collective, but
robust.
it's
So what
it's
encoding
like
do you
n
use
to
here
the 3
for
halves or
your
something
space?
instead of n squared.
In the case we were talking, I mean, in this case where
I think it's actually the
spin
exponent.
1 half,
Oh.
I mean, it was for
There's like
Adam's
certain terms in the
experiment.
density.
Okay.
1 is 0, I mean, in
So like
hyperfine-
hyperfine states or
Uh,
two
triple
redundant
zero.
states?
Semi data and
Triple
like
zero.
that's
This
exactly
was
what happens.
this
So yeah,
the
the
no,
narrative
these
can
are
be something
these are
to do with, like,
no, I mean the representation is adiabatically eliminated.
Yeah.
Yeah.
So
clearing up
this
defects,
gives me just I mean, but anything that you do Rydberg tracing,
Yeah.
in principle,
I mean, the point about Rydberg pricing
Yeah, yeah.
is that you only get this effective soft core potential
Yeah.
in the like the spin
Ah, I
states,
see. Okay.
basically.
Oh, so the trick is to take this thing and then apply like the strong spin locking thing.
yes,
and then
but
just-
this
But
thing,
yeah,
this
I guess
string
you guys
here
talked about being
Yeah.
15 years.
plus the fact that you have an SY model.
Mhm.
It's so robust. I mean, we
Oh,
were
okay,
surprised
interesting.
how good it works. I mean,
Yeah.
we can create almost an all-to-all squeezing, even when you go. I mean, even with the Rydberg rotation here is 2. When you have a large system, it becomes like an all-to-all of all the system.
I see.
Yeah.
Okay. Interesting. Yeah. So this is what you guys used in this recent squeezing paper.
No, this is different, and because Adam could not do that. So no, in the current experiment, what he did was he went outside the blockade and go in an intermediate thing that is hard to model theoretically.
Is this in Jeremy's
This is
paper?
in Jeremy's
Okay, so
paper.
I thought about
Okay.
okay,
Yes,
so I
this
know
is
the
in
paper
Jeremy's.
actually.
Yes,
So
yes.
enhancing with squeezing
Exactly,
with Rydberg pricing.
exactly. That's where we were so surprised that it was.
Yeah. So it's very robust.
It's very
Okay.
robust. Yes, so
I
you
mean, I
could
never
try.
make this connection between reading this paper and our problem, but I mean, I agree actually that it's the same question. in a
Yeah.
sense.
The same question. You want to make everything collective.
Yes.
So
And it's interesting because I guess like for us we use these optimizers, but we're also doing like the driving between these two states at the same time as the driving between these two
oh,
states.
okay, I see.
But I guess this is like, you know, kind of a more static version.
Exactly, yes, exactly. It's also rotating wave, I mean, because, I mean, this is large, so this Hamiltonian is in the rotating wave approximation that you are throwing out different terms.
It's interesting. Did you guys also think about how to maybe like get rid of this part? I know for squeezing, you know, this is. But I guess then.
I mean, if you want to do this thing, you can do rotations
The
that
flocking
that
type?
the flocking that you have this, then YY CC,
Yeah.
and
Then
that's
you
it.
cover everything.
Not knowing how to check it.
Okay, very interesting.
It could be interesting to compare somehow, right? I mean,
Yeah. No, it seems like it's a very good suggestion.
Yes.
Definitely something we should.
Something
Could be interesting. I mean, if it's easier, that could be useful.
absolutely, yeah.
And what I was thinking when you were mentioning, maybe something that we could do also is if you have an alkaline atom, if you put the atoms in the lowest band, then you can also have, because the wave function,
the first thing is
yeah, so well, you can, there is exchange interactions between the atoms.
that we didn't think of in the systematics.
If you have the atoms here, because of Pauli statistics, I mean, this is I mean not this is how you look energetically in different levels. Then if you look at quantum interaction between the atoms, it's the form S of S. So you can make the system also lock to a large spin.
This is just natural interaction between
Natural because yes, exactly. So you have.
I guess this is how actually the electrons interact.
Exactly.
Yeah, that's sort of the process why
exactly. That's what your law is. You are fully spin polarized, and this is non-interactive. And if you are going to flip one spin, it costs interaction energy. So you don't do it.
Yes.
So maybe this could be another way that you have the atoms in a trap, and then you can make them interact by hopping. If you let this super exchange and then come back, typically because if the interactions are strong here, you are not going to come back to another S because it costs energy. So you can do this.
They will be locked to their respective sort of level.
Exactly. And SU2, I mean, the interactions are SUN, so you guarantee that are on the form all these S dot S type, even higher order pairs. So that could be an interesting. I have not thought about that. And in addition, you can try to modify the form of the interaction by adding some spin orbit coupling. So if you have a laser that, for example, this is the lattice and your laser is along this direction, then what happens is that you start to, I can do it for spin 1/2, for example, even. So if you have these two levels, yes, up and down, up and down. So if you have a drive, for example, then drive is even larger than interaction. Then, for example, if the drive is along the x direction, your states are going to be plus x and minus x of the spin 1/2. Now, if the drive changes the phase, for example, it changes by pi, it's the opposite. So, and therefore, here, because when you are going to tunnel back and forth, you can, if you have an atom, imagine that you have an atom here, and then you are going to do the super exchange. So you are going to, you are only going to go here, but this is energetically costly because when you go here, you gain energy U, but also you gain energy of the drive. So this is U plus omega. On the other hand, if you start the opposite situation where this atom is here and you are here, if you tunnel, then you decrease omega. So you have to minus. So you see that this process is forbidden, and instead of having S dot S, you can have SCSE. So collectively, so you can tune the form of the interactions and make the coupling constant by changing the phase of your laser. So it could be an interesting way that might lead to other type of
different experimental settings.
Different experimental settings, yes. I mean, these are very long-lived and
it's true. And actually might avoid a lot of the issues with like trying to excite multiple atoms in different directions.
Yes, exactly. So it's natural locking of the atoms into.
Have you guys also explored this type of scheme in a paper?
We have explored this type of scheme for modifying the interactions in a paper for spin 1/2 atoms, but we are thinking to see how we can generalize it to higher end, and because it becomes your interactions, it becomes we have SUN interactions, so SUN interactions becomes and in terms of spin, these are raising and lower operators of the spin. In terms of large spin operators, it becomes for all of possible terms with a specific coefficient. So we were working, what are these coefficients good for?
Yeah. And actually, I mean, so in these chemistry contexts, these higher order terms are like actually pretty important.
Yeah. So that's what they always say. Like when we discuss with them and we show them, yeah, we can do Heisenberg. They were like, that's not enough. We need more. So yeah.
Okay, we could think about that because this can be really tuned by the couplings that you have here, and even if you start to break and do SDLC, I don't know if they like that.
That's also and more if you have something that can generate the anisotropy.
Yes,
really like the internal fields and the
yes, exactly. Then it becomes a highly tunable
model. So adding spinor coupling to the game server.
To the game to tune. I mean, if you don't, you have only S.S interaction, but if you start to.
But the prefactors change basically.
Yes, exactly. You can change or tilting. I mean, if you tilt. Then you keep SUN, but the point is that now it's an energy cost. I mean, if you have one atom here, and you are going to have one atom here, and it's tuneless, then this process has U minus delta, U plus delta. And in the other, when it is the other way around, you have U minus delta. So you change the strength of the coupling by changing the height of the spacing of the height, the external potential field, or you can use a parabolic potential that controls the height.
Yeah. Interesting.
Yeah, that could be. That
makes a lot of sense actually.
No, I'm looking forward to
an eraser.
I guess
it's okay. I see some paper towels.
So that's for the hand. No, but that's really like, I think we should think a little more along these lines because
I mean, especially for the bigger brocade, maybe if you don't have to do anything but just drive that. I mean, of course the experiment is more difficult and Adam could not do the drive because.
So what are the time scales like there? Actually, like, because that's what we were discussing, like
so the experimentalists have told me like their typical Raman timescales within the hyperfine states is pretty comparable to the Rydberg-Rabi frequency. So
no, it depends. I mean, for alkaline atoms, this drive is hard to get.
Okay.
Because it is a forbidden transition.
Yeah.
In atom experiment,
it's much harder.
It's kilohertz, and the drive for the rigor is megahertz. But there are other atoms where in rubidium,
they
you
can
do it. You can do it
tune
comparable.
them.
Yes, because they are not nuclear spin, but I mean, are not forbidden transition.
You can actually just drive them basically.
Yes.
Yeah. I think in the lab they use a Raman transition for their.
Okay. That would be good.
Yeah. So that's definitely something to compare against.
Yeah.
And then also this the like collisional type interaction.
That could be very nice. I mean, they have seen no losses because, of course, one of the questions is how bad is your going to be if you have many atoms in a trap, if they're going to be lost. But no. Three body or five body losses have not been seen significant. So I of course spin yes, then in principle.
It could work. Yeah.
Okay.
Thank you so much.
Bye.
Okay.
It is kind of cool.
Yeah. It would be worth exploring. We can test it out.
Yeah.
What's wrong? What do I follow you? Yeah, the posters. I have to find them myself.
No one wants to get lost.
Oh, okay. We go this one. This is good.
My step one.
There we go. Success, yeah. Wow, that was quick. Let's see where we go.